as far as teaching is concerned, so he worked many institute in Gujarat. So starting from okay, there are several institute. So just to say name, he also worked in Nirma University, Gujarat. Then Babaria Institute, CK Pithawala College of Engineering, Pune. Okay. So sir has as far as teaching is concerned, he is well versed with teaching communicating. And about research, we don't have to say that he is already mastered in research. Have several good number of papers. He also won the Excellence in Thesis PhD award at IIT Bombay in August 2015. Plus, he also have a top 5 most downloaded paper in 2013 in IMAKE Part A, Journal of Power and Engineering. Okay. So he has very good publications and his work on turbomachinery is really recommendable. So, sir, thank you very much for accepting our invitation, and I hope your knowledge on turbomachinery will encourage student, and particularly we can say that to start work in at least in turbomachinery field, because turbomachinery is very difficult. Okay, if you start say as compared to real PSD, real incompressible flows, straight flows, flow over this thing, flow in a constant channel is really tough actually. Yeah, sir.
Yes, yes.
So, sir, is session is over to you. You may start,
Yeah,
please.
yeah. Thank you, Dr. Sanawane. Uh, Thank you very much for your introduction. Say today we will be having talk in say applications and challenges of CFD analysis in turbo machinery. Let me check with like whether the
Yeah.
screen is visible to you. Okay.
Yes, sir. Screen is visible to me. Sir, one more request, which we try yesterday. You can use the pointer which is available here. So if you can just click on the right click, and that so that
Yeah. Okay.
pointer is there. No, pointer option laser.
Yeah. Okay.
So
Fine.
that will so what you are talking on and where you are talking, that will help the participant. Acha, I have a small announcement for participant. Uh, Please mute your mic during sessions. If you have any questions, either you can write in the chat box, or either you can have at the end of session. We'll take a question and answer session. That time you can switch on your audio and then you can talk and you can ask your questions. Absolutely no problem. Sir, over to you, sir.
Yeah. Fine. Thank you. Thank you very much. So I don't think there is a need of video now. So I have shared my screen, so that will save your data and everything. Let's start with.
Yes, sir.
Okay. So the topic it is on say, applications and challenges of CFD analysis for turbo machines. So if you are talking in terms of turbo machines, always the question will start with like, it's a very complex device. Yes, it is. It is having wide scope of applications. We will see. Yes, it has. And for that, we are looking for say CFD analysis. So let's see like what all I have in terms of my presentation. Okay, so my content, if you look at, that's what is saying say introduction and fundamentals of turbo machines, because say when we are starting with the CFD analysis part, you must be aware of what we are talking of and for what we are looking for. Okay, then it asks for say questions saying like understanding of CFD application particular to the turbo machines. The question always will arise, why we need to do this CFD analysis. Yes. Next question always will arise, what all need to be understood by me so that I can do this CFD analysis for turbo machines. Next question always will come, if I have all this background, how to do that part. Okay, so we will be talking in terms of say this CSD application to turbo machines by saying say why, what and how. Then after I'll be discussing about few case studies with various aspects, my own work as well as the work from others. Okay, so that will give you some idea in terms of what all are the applications in terms of CFD. Then we will be discussing about what all are the advantages of CFD in turbo machines. Then we will be discussing about say issues and challenges of this CFD application to turbo machines, and then we will explore with say next generation CFD demands. So this all will be covering within 3 hours period. Okay, this area of turbo machining is so vast, maybe it will take say hours for the discussion, but I will try to condense that. So the beginners, I hope most of the participants they are say faculty members, maybe PhD scholars or MTech scholars, or maybe from some industry. So they already know something, or maybe I will try to add something, or maybe I will give ignition to them. That's what is my perspective always being a faculty member in IIT. So the thing is how we need to handle, how we need to understand the problem. That's what is very important. And then after we need to give the solution to that problem. Okay. So let's see. Suppose if I consider in terms of say applications, so turbo machines, if I say, that's what is starting from the morning, saying your vacuum cleaner, the fan what you are using. Now people they started using say computers, laptops, so that's where we are having say computer cooling fans, radiator, that's what you are using in car, say your air conditioning system. This is what is a special device you might have understood. Say this is what is a device, that's what is being used by dentist in order to make the dent in your teeth. Okay, and if you get the cut section inside, you know that's what is made up of turbine. So this is what is also a turbo machines application. The anyway the pump, that's what it is common device to you all, those who are working industry, for them also it's a very common device. Okay, let me move it. Suppose if I am talking in terms of your power plants, we are having cooling towers. In order to have this cooling, you need to have big size fan. If you look at, that is nothing but it's an application of turbo machines. If you look at say there are few flow meters, they are known as say turbine flow meter. That's what is being used for the measurement of mass flow rate for various liquid as well as for gases. Okay, you are having say big size centrifugal compressor, that's what is having say some purpose of say transportation, some purpose in terms of high pressure requirement. We are having say gas turbine power plant, that's nothing but land based power plant. We are having steam turbine power plant, we are having say hydro turbines. You know, if you look at, if you start searching for what are the applications of turbo machines, you will find everywhere. If you start with very small device, that is also made up of turbo machines. Let's see next. This is what is a major application what we can say in terms of say aero industries. For aero industries, this gas turbine engines what we say, they are the thrust generating device, and that's what is a turbo machinery device. If you look at on the rear side, in order to run all your auxiliary devices, controllers, everything within this aircraft, we are looking for say this engine. That engine is nothing but it's a power unit. Here if you look at, this is what is your turbocharger, maybe your turbocharger, that's what we are using for your IC engine, maybe for say high application in terms of heavy vehicles. This is what is the application what we say these days people they are talking in terms of say high bypass ratio engines. Okay, so this is what is a high bypass ratio engine, that's what we are using with. Now, as I told, like day by day, demand and the expectations, that's what is always increasing. And let me share you, not being working in aerospace engineering department, I say, you know, aerospace engineering is one who has given thought to everybody to think in a different perspective. If you are looking for what is a major requirement, we say we always looking for say compactness. Next, we are always looking for something that's what is lightweight. You know, like that's what has given idea to many. For many other applications, they are started thinking in sense we need to have things to be compact, we need to have things to be lightweight. Okay, so if you look at here, this is what is a small engine. This engines, that is also gas turbine engine, and that's what is being used for now UAVs and MAVs. Okay, if you look at, this is what is a gas turbine engine, that's what is developed by Onera. The thing is, you know, these days people they are looking for say electrification in science, like we are using say lithium ion batteries. Okay, slowly what we are doing electrification by users using so solar applications. Now in order to store this energy, we are looking for batteries, and if my power capacity is higher, then you can understand the size of my batteries will be increasing, so it may be constrained somewhere. So in order to replace those batteries, people they started using this miniature kind of devices. This is nothing but miniature, say, gas turbine engine. You can see here we are having, say, 10 mm diameter rotor. This is what is a work, that's what is done by, say, MIT gas turbine laboratory. If you are looking for, it is having, say, 8 mm diameter centrifugal machine. Okay, that's having, say, 4 mm diameter radial inflow gas turbine. You can imagine we are having, say, micro size to, say, mega size. You can understand. Say if I am talking in terms of, say, specific applications, you say here we are having, say, few mm's, and when I am talking in terms of, say, aero engine or land based power plants, that's what is coming in terms of, say, meters, maybe 2 meter diameter, 2.4 meter diameter. So that's what all aspects we have in terms of our turbo machines. Say people they talk in terms of, say, some space applications. There also we are having, say, pumps as well as turbines. That's what is having, say, special application for the propulsion. That's what is giving very high amount of thrust. That's what is required for the transportation purpose. If you look at here, we are having non-renewable sources of energy. We can have, say, tidal turbines, we can have, say, wind turbines. So just look at, like when you wake up in the morning, and if you start thinking of, let me have turbo machines as my device, you will find everywhere all these devices, they are made up of turbo machines. Now that's what is the whole scope of turbo machinery. Now let's try to understand what exactly this turbo machines is. Many of you may be aware of, but let me put in words. It says it is any energy transferred to or from continuous flowing fluid. You need to understand we are talking about the flowing fluid. That's what is continuously flowing, and by dynamic action of one or more moving blades. Okay, so if I classify these turbines, say turbo machines, they have been classified as based on, say, function. What it say? Power absorbing device. Maybe that's what is required for rising of pressure, or that's what is required for, say, rising of heat in terms of pump. So compressors and pumps, they are, say, power absorbing device. Same way when I say power generating device, they are mainly defined as, say, turbines. Now next, if I say flow direction, it may be, say, axial direction, it may be centrifugal or radial direction, it may be mixed flow. It's a combination of both axial as well as, say, radial combination. Now based on flow physics, what we say, what kind of fluid we are using for this purpose. We are using, say, compressible fluid flow, say air, gas, refrigerant, maybe steam. That's what is coming under, say, compressible flow machines. When I'm talking in terms of incompressible flow machines, we can say we are having steam, we are having water. That's what we can consider as, say, incompressible flow. This is just small idea in terms of what all we are looking in terms of analyzing. So you need to have platform, you need to have base, and this is what is giving the base. So purpose, like working fluid, then the flow direction, all these terminologies that will come, that will be helpful for us when we are understanding, say, applications. Now let me tell you, like, if I go for, as I told, if I'll be continuing talking in terms of, say, turbo machines, then it need days. Okay, say main application for CFD, let me share you, say in 70s, people they started using CFD analysis. In presentation also it will come. They started using, say, CFD for analyzing the fluid flow, mainly for aerospace application, mainly for gas turbine engines. Okay, and slowly the maturity that has come with the technology, now people they started using this for some other applications also. But CFD in turbo machinery mainly been applied for, say, aero engines. So let's see, like, what all we understand in terms of, say, engines. We are having two kinds of engines, say air breathing engine, non-air breathing engine. Okay, yeah, this classification it's very general. I can say I'm having, say, jet engine, in which I can have say ramjet engine, scramjet engine, pulse jet engine, say I can have say gas turbine engine, turbo ramjet, rocket jet engine. But major concern, that's what is with say gas turbine engines. So if you are looking at, again it is been classified in sense, say maybe it's a turbojet engine, turboprop engine, turbo shaft engine, maybe turbofan engine. We can have say unducted turbofan, ducted turbofan engine. Again this turbofan engine, that's what has been classified in say so many things. So you can understand what is the requirement of gas turbine engines. And all this device, if you look at, that's what is say prefixed by turbo. That means it's a turbine or it's a turbo device. That's what is being used for gas turbine applications. So whole my presentation, I will try to incorporate maximum in terms of devices what we are using for say engines, gas turbine engines. I will discuss few applications for other applications also, but my major focus will be on these devices. Okay, let's say this all are the new developments. You can see this is what is a high bypass ratio engine. This is what is developed by GE and Honda. What it says, I'm having big size fan, then I'm having compressor, I'm having centrifugal compressor, then I'm having turbines. So if you look at here, this is what is a recent project. That's what is going on in Europe, in which they are using your fundamentals of thermodynamics, and what they are doing is they are doing intercooling of air leaving from say first compressor before entering into the second compressor. Then after what gas that will be coming out, that's what is having say very high temperature. That high temperature unnecessarily we are wasting if it is going to atmosphere directly. So what they are doing reheating here. So this is the kind of application now people they started thinking of. Here if you look at, this is what is my fifth generation engine. That's nothing but your F-35, very recent engine developed by say US. That's what is having say counter rotating technology. You can understand the size of my engine. These days people they started working on this advanced engine, in which it's having say special requirement. Day by day the expectations from the engines, that's what is changing. So we have first generation engine, second generation engine, third generation engine. This is what is next coming, that's what is say sixth generation engine. Okay, parallelly people they are working on say unducted fan. So this is what has been developed by say GE. That's what is say unducted counter rotating fan. Say there is a project, that's what is going on in collaboration with Russia and Europe. That's what is a Volta say vital project that is having say this multi-stage, and that's what is having say counter rotating technology. So you can understand, like, with maturity of technology and the requirement, day by day you need to do more and more research, and this research activity requires more efforts, and for putting more efforts you need to have more understanding, and for more understanding you need to have more reading. Okay, let's move to the next. Say let me start with say this is what is I was showing in sense say high bypass ratio turbofan engine. So here we are having big size fan, that's nothing but axial fan. Here somewhere I am having say intermediate pressure compressor. This is what is say HP compressor. That HP compressor that can be run by your HP turbine. So here there are two spools, that's what is placed inside. So my HP turbine spool, that's what is rotating my HP compressor. This is what is say LP turbine. So LP turbine, that's what is rotating my LP compressor. Okay, so if I will take this blade, so it's looking like this. Like this blade, if I put the cut section at some place, that's what is having say aerofoil shape. Okay, this is what is having say aerofoil shape. That means what fan, compressor, turbine I have, they are having say aerofoil sections. Okay, so here if you look at, this is what is the rear compressor stage. Now just try to understand here what is the case. This is what is my entry area, and this is what is my exit area. So observation is, if you look at, my exit area A2, that's what is say larger. So what it means, I am having this passage as diverging passage. So what it does, diverging in the sense, that's what is increasing the pressure. In sense, at inlet I am having say some pressure P1, at exit I am having some pressure say P2. So this P2 that will be greater than that of my P1. Now whole blade if I put and if I do the skeleton, what it says, it is comprising of number of diffusers. Okay, so the flow passage between this blade, if you look at, it is a diffusing passage. So now you need to understand what is the purpose of compressor. Say the purpose of compressor, it is to compress the air, to rise the pressure. Okay, now this compressed air that will increase your pressure as well as temperature. That's what is my requirement for combustion chamber, where your fuel and air that will get burned. Okay, after this burning, it will generate very high enthalpy, very high internal energy. That's what is being passed through this turbine. Okay, that means this flue gas, that's what is coming out from combustor, that will rotate this turbine. And this turbine, that's what is connected with your compressor. That means this compressor that will get rotated by using the turbine. So you can understand, say the purpose of compressor is to compress the air, and purpose of turbine it is to rotate the compressor. Okay, so when I am talking in terms of say aero engines, this is what is my requirement. The main requirement for aero engine, it is to generate the thrust. Okay, it is not to generate the power. When I am talking in terms of say land based power plant, I will be having additional stage of turbine. That turbine that will be connected with your generator, and that generator will generate your electricity. But there also purpose of your turbine, it is to rotate your compressor. So now we need to understand what we have in terms of compressor or compressor blade. It is comprising of number of aerofoils. This is what is one cut section. I can have one aerofoil here, I can have second aerofoil, like that. I'll be having maybe different aerofoils. Okay, so that's what is very important for us to understand. Okay, now here if you look carefully, what is happening, I'm having this passage area, that's what is decreasing. And if I look at the turbine, my passage area, that's what is increasing. So the whole purpose, what it says, my continuity for any device that must be satisfied. What my continuity says, when I say my continuity, then mass flow rate, it is given by say your density into area into velocity. Now for this axial machines, my axial velocity that remains constant. Okay, now when I'm raising my pressure, what is happening, say pressure and density, they both are say P is equal to rho RT. That means my density also is changing. Okay, when my density, that's what is changing, you can say with rise of pressure my density is say decreasing. Now in order to increase in order to maintain my velocity to be constant, my area need to be decreased. Okay, so pressure and density, they are in direct relation. So that's the reason why this area, that's what we say, it is a decreasing area. It may be having say different concepts. Say this is what is my hub and constant tip configuration, this is what is my hub and this is variable tip configuration. I can have say constant mean diameter configuration, I can have combination. You will say, sir, like we are talking in terms of say analysis, CFD analysis of turbo machines, and you are talking of all this say aerodynamics part. But you know, like this is what will be helpful, and this is what is making your flow through turbo machines very complex. We will see one by one. Okay, so as I told, we are having say aerodynamic device. That aerodynamic device, I can say it's a aerofoil. Okay, so here if you look at, this is what we say as say low cambered aerofoil, because my turning or the bending or say this delta beta, that's what is low. If you are looking at say second, that's what is called say highly cambered aerofoil. Now these two both have say special application. What is the purpose of my aerofoil? It says it is to generate the lift. If you ask any aerodynamist, if you ask someone who is working in fluid mechanics, he will say the whole purpose of this, it is to generate the lift. Okay. Now, when I say it is to generate the lift, then you will say, sir, then why are we using this in turbo machines? We need to take benefit of this lift. So I say, if I look at this aerofoil, that's what is generating lift as well as drag. Okay, so lift, it is of my requirement. Here, if you look at, I'm having say passage, one of the cut section in which my inlet area is lower, my outlet area is greater. Same way, other configuration, if you are looking at, I'm having my inlet area to be higher, my exit area to be lower. So we can say this is what is a passage, that's what is called diffusing passage, and this is what is like looking like a nozzle, that's why it is called say conversion passage. Okay, now say this is what we say in sense we are having say this is as one of the device. Okay, now here what we have understood, this is what is showing the direction of rotation for both compressor as well as turbine. So what we can say here, my compressor blade, that's what is rotating from this upper surface, that's what we say as suction surface, and this lower surface what we say as a pressure surface. So here this is what is my suction surface, this is what is my pressure surface. So what it will do, it will be rotating from pressure side to the say from suction side to the pressure side. Now what we know, this is what is my lifting force. Now the compressor is a device, it's a power consuming device, because what is our purpose, we want to compress the air. Now in order to compress the air, what you need to do, you need to do work on your working fluid. So what we will be doing, say if I am giving the direction of rotation in this way, I can utilize my lift force for the compression work. Similarly, if you are looking for say expansion or say turbine, here also I am having say my lifting force. So what I am doing, I am utilizing this lifting force to accelerate my flow. That's what is my requirement for the turbine. So this is what is a whole purpose, what we say in terms of say aerofoils. Now these are some of the aerofoils what we are using for our purpose, say compressor. Say they are C4 aerofoil, control diffusion aerofoil, NACA aerofoil, double circular arc. You can see I'm having two circles, one circle downside, pressure surface, one circle upside, that's what is a suction surface. I can have multiple circular arc. You can understand here I'm having say this arc to be differently made. I can have this S-type aerofoils. So what it says, the upper aerofoils, they are mainly been defined as say subsonic blades or subsonic aerofoils, and lower side, that's what is called say transonic blade or transonic aerofoils. Now let's try to understand what is happening. What is the purpose of aerofoil? As I say, the purpose of aerofoil, it is to generate the lift, and that lift force we are using for compressing our air or say gas. So here if you look at, I'm having my suction surface, I'm having my pressure surface. Now this is what is representing my velocity distribution on pressure and suction surface. So if you are looking at the suction surface, initially I'll be having the acceleration of my flow, and then after my flow is getting decelerated. Similarly, if you observe near my pressure surface, what is happening? My pressure, my flow is accelerating up to certain distance, and then that's what is getting decelerated. So this is what is representing say distribution of my velocity or velocity change along the chord. Same I can represent in terms of Cp. That's nothing but the coefficient of pressure. So this upper line, that's what is representing my Cp or pressure on pressure side. So what we know from our fundamentals, on pressure side I'll be having higher pressure, on my suction side I'll be having say lower pressure. And here what I was saying in terms of this is what is showing my acceleration process. When I'm having my flow to be accelerated, my pressure is decreasing. When my flow is decelerating, that time I'll be having my rise of pressure. Similarly here, this is what is my acceleration of pressure, and this is what is my deceleration of pressure. And if you look at the area under this curve, that's what is representing your work done. Okay, this is what is very important. That's what we need to understand. Okay, so this is what is, say, representing my work done. So good aerofoil, we can say good aerofoil in sense my requirement of work done, it should have this area under the curve to be as high as possible. Okay, now let's move with what is happening with your aerofoil. So this is what is, I'll not be taking much time in terms of your velocity triangle, but still let me say this is what is, say, your blade angle beta 1. My flow is entering axially. This is what is my rotational direction. So that's what is representing my beta 1. Okay. Same way, if you look at here, say this is what is the exit of my rotor, that's what is coming out with blade angle beta 2, and this is what is my stator. Okay, so you can say I am having this as my velocity triangle at some of the location. Now with change of my mass flow rate, when I say change of mass flow rate, that's nothing but my density into area into velocity. So you need to understand, if I'm reducing my mass flow rate, that means if I say my density is not changing and my area also is within the passage is constant, then my axial velocity, that's what is decreasing. So what it will do, my axial velocity is decreasing, my rotational speed is same, so I'll be having my beta angle to be changed. Reverse case, suppose say if I am increasing my mass flow rate, my axial velocity is increasing, so my beta angle, that will be changing. Same thing that will be happening, what we say is, in terms it is called, say, incidence increase and incidence decrease. Similarly, if I am talking at the exit, that angle I am writing in deviation increase and deviation decrease. Now this is what is a characteristic of my aerofoil. This is what is representing CD curve. What it says, like if I am moving with my positive incidence angle, okay, then my drag force, that's what is increasing. If I am moving beyond certain angle, then my drag force, that's what is increasing. So in this particular region only, I will be having my drag to be minimum. When I say my drag to be minimum, you can understand this is what is representing lift. What it says, my lift, that's what is higher in this particular region. Okay, so when you are operating your compressor, that time you need to be careful with the change of this. This will be the background for my next stage. Let's see. Now, as I told, what is happening, say when I'm having, say, my incidence angle 0, this is what is representing my distribution of, say, Mach number, or we can say pressure. So this is what is my work done. Now what is happening, if I'll be having positive incidence angle, my work done, that's what is increasing. If I'll be having negative incidence angle, then my work done, that's what is decreasing. So same thing here, if you look at positive incidence angle, negative incidence angle for two different kinds of aerofoils. Here if you look at, this is what is representing my thickness ratio. That means what is the maximum thickness of my aerofoil and how my CP is changing. So you can understand this CP, it is mainly been useful to us in sense of understanding when we are having, say, these aerofoils. Let me move it, say, next. Say we are having this device, we can say it's a prime mover. In that work done, we are writing in terms of, say, aerodynamic work and mechanical. So if I consider, say, 100%, what I'll be considering, say 2% around loss, that will be with shaft losses, it may be disc friction loss or maybe bearing loss. Say stage, I can say 98% that need to be the work I need to extract from the stage, say rotor and stator combination. Out of that, 9%, that's what is getting lost in the rotor only. That's what I say rotor aerodynamic loss. Now remaining, say, 7%, that will be lost in my stator, and I'll be having my isentropic efficiency to be around 82%. Now let's try to understand Now I am making the background for our CFD analysis. Just try to understand. Say this is what is representing, this is what is, say, mechanical part we are not bothering of. We are not interested in at this moment. Let mechanical engineers to thought of that. Now being an aerodynamic engineer or maybe being a designer, what is my expectation? I say I need to have increase in this efficiency. So let me tell you, like if you ask 10 years back, if I say my efficiency is 82%, people they were happy with. Now the expectation has changed. They say we are looking for say compressor that will be having efficiency more than this. Maybe you can increase the efficiency by 84%. Now what I need to do, I say my task is to increase this efficiency. If I want to increase this efficiency, then I need to play with these numbers. When I say I need to play with these numbers, what I need to do, I need to minimize the losses. That's what is happening. If by some mean, if I can reduce the losses, that's what is happening inside my device, I can improve my efficiency. And that's what is the whole business in terms of our CFD. Okay, so let's see. Like this, all are the sources of say losses in my axial flow compressor. What I say, it may be say end wall losses, profile losses, tip clearance losses, secondary losses, shock loss, shock boundary layer interaction. Let's see one by one. Suppose if I say in terms of say end wall losses, what all we know is whenever I am having solid body and my fluid is flowing over that, because of viscous effect, we will be having the growth of boundary layer. So if you consider say a compressor as a device, then that's what is enclosed inside the casing. So casing is a solid body. So along the length, my boundary layer that will be growing downstream. Same way, if I consider I have my blade, that blade is nothing but it's a solid body. When I say it is a solid body, it will be having, say it is subjected to growth of boundary layer because of viscous effect. Now what is happening? Say my flow, that's what is incident on this blade. Okay, this is what is representing my turning. You can say if I want to have my flow to be compressed, say P1 to P2. Say here it is P1 and here it is P2. That means my compressor blade or compressor blade aerofoil, it is subjected to adverse pressure gradient. When I say it is subjected to adverse pressure gradient, my downstream pressure is higher. There are more chances for my flow to get separated under adverse pressure gradient condition. And that's the reason why if you look at here, this is what is showing the separation of my flow. Okay, so the growth of this boundary layer, what we say, that's what is playing important role. What is said, like the losses because of boundary layer cannot be avoided, but it can be minimized. Okay, we can minimize that part. We cannot avoid that situation. Let's say, suppose I was talking to you in terms of say two different cambered aerofoils. One is say low cambered aerofoil, second it is say high cambered aerofoil. When I say low cambered aerofoil, the wake is nothing but it is like deficit of your velocity. There is a presence of low momentum fluid near your trailing edge, and that's what if I'll be measuring my say velocity profile at the exit, it will be giving you the deficit of your velocity, and that's what we are defining as a wake. When I am having say low cambered aerofoil, I am having say thin wake. If I am talking in terms of say like high cambered aerofoil, I'll be having thick wake. Okay, now let's see. Say when I say I'll be having say high cambered aerofoil, I'll be having thick aerofoils. There are more losses. That's what is subjected to. If I'm talking about say thin aerofoils, the losses are lower, but you know, like my lifting capacity also will be lower. So my work done capacity that will be lower. So you need to understand when I say when we are having say highly cambered aerofoil, we can generate more amount of work done. That's what is my requirement. But when I'm increasing my cambered, what is happening? I'm having the chances for my flow to get separated. Why it is getting separated? Because it is working under adverse pressure gradient. So the profile loss, what we say, this is nothing but this is what is called profile loss. That's what is depending on your Reynolds number, your Mach number, the longitudinal curvature of the blade, inlet turbulence, free stream unsteadiness, and resulting unsteady boundary layer, pressure gradient, shock strength, so many parameters. That's what is depending, or say your profile loss, that's what is depend on. If I consider say my blade parameters, then what is my thickness, what is my camber angle, solidity, sweep, skewness of the blade, stagger angle, blade roughness, all these parameter, that's what is affecting my profile loss. So you need to understand, if I want to minimize this profile loss, I need to play with this many parameters. Okay, so I need to have understanding of all these things. Let's see, let's move towards the next. Now what we know, like suppose say this is what is my casing and this is what is my rotor. So now my rotor need to rotate freely. So if I want to have my rotor to rotor freely, I need to provide certain amount of clearance between casing and rotor. If I say stator, that can be connected from hub to say this casing, but I need to have certain amount of clearance. Now what we know, like I'll be having differential pressure. So I'm having say high pressure and low pressure. And if I'll be giving some clearance, what will happen? My fluid will try to jump from high pressure side to low pressure side. So it will jump from high pressure side to low pressure side. So you can see like my flow is flowing from high pressure side to low pressure side. What it is doing? It is giving rise of flow blockage. Okay, now what is happening? I'm having my incoming flow, that's what is being combined with my tip clearance flow, and that together combinedly what it is giving this kind of structure. This is nothing but that's what has been captured by CFD analysis, and based on that authors they have given this as a model. What it say, it is depending on how my blades are being designed, how my blade aerofoil, it is there near the tip region. So here if you look at what is happening, I'm having my incoming flow, that's what is flowing inside. So the flow, that's what is coming out from my trailing edge, it will try to move back, and this is what is making my complex structure. Similarly here if you look at, hello,
Yes, sir. You're audible.
yeah,
Go on.
yeah, yes.
We are listening.
Okay. So let's see, if you are looking for this kind of configuration, what is happening? I'll be having my flow that's having a different pattern. Now, when we are doing our design, that time this flow physics, it is not in detail understood by anyone. It depends, as I told, it depends on so many parameters. So this CFD tool, that's what people they are using in order to understand this kind of flow physics. And based on this understanding, they are modifying their design such that they can minimize the leakage losses or tip leakage loss. Here, if you look at what is happening, because this low momentum fluid, that's what is coming out here, that will be striking on my stator. Okay, if I say that's what is striking on my rotor, what is say on my stator, what is happening, this stator that will not work as per my design condition. Okay, okay, so this is what is one of the contributor to the loss. Say we discuss about profile loss, we discuss about tip clearance loss. Let me show you the actual picture. That's what is happening in the rotor. So this is what we can say, we are having blade, and that's what is being placed on the hub. So as we know, this is what is my solid body. So I'll be having the growth of boundary layer along the hub. Okay, so from both the surface, say pressure surface and suction surface, I'll be having growth of boundary layer. Then I'm having say the tip leakage flow, that's what is flowing from pressure side to the suction side. Now, when the flow it is striking here, it is making say horseshoe vortex. That's what is moving, it is rolling and it is moving like say corner vortex like this. Now here in this case, if you are looking at, since we are having high pressure on pressure surface, we are having low pressure on suction surface. So there is a differential pressure. And because of this differential pressure, I'll be having flow to be rotating like this. And my incoming flow or main flow, that's what is coming. So you can say in between the passage, I'll be having the flow structure like this. Center portion, that's what is say core region. Outside, if you are looking at, I'll be having all kind of physics. Say here I'm having say tip leakage flow. I can say this end wall interaction, that's what is happening. Here in this case, say this is what is my shear layer, that's what is rotating. And this all together, that's what is making whole my flow physics. That's what is very complex. And what is our target? Suppose say if I say I'm given a task to design the compressor, then I will look at all this flow physics, and based on my understanding I will try to minimize these losses. If I'm able to minimize these losses, I can improve my efficiency. Okay, or suppose say you are joining a company, or you are working with a company, or you are doing say analysis for already existing say compressor blades, then you need to analyze this part and try to understand what all are the problems with this blade, and based on that you need to give the suggestions for the modification. So this is what is making the whole interest in terms of turbo machines. When we are talking of, you can understand till 60s people they were doing design, that's what is based on say experimental work. Then like day by day requirement and their expectations that has increased, as I told, and that's what has given say initiation or ignition to say numeric persons to start developing the code. And those codes, like it is not that easy task to develop the code for analyzing turbo machinery. You can understand up till now whatever CFD analysis you might have done, maybe flow through duct, maybe flow through some passage or something like that. But when you are looking at, you need to have great understanding of this whole flow physics. Until and unless you are having the understanding of this physics, you cannot move forward. And that's what is a big challenge even as on today for the person who is doing design, person who is doing CFD analysis, person who is doing experimentation, and person those who are using that device. Okay. Now, in terms of say incidence angle, what I was talking, say this is what is representing my change of incidence angle. Here, if you look at, when I'll be having say positive incidence angle, I'll be having my flow separation, that's what is happening on suction surface. If I'll be having say negative incidence angle, I'll be having flow separation, that's what is happening on my pressure surface. And this is what I already discussed with, this is what is my design condition. If I'm moving away from design condition, say positive incidence or negative incidence, like when I say positive incidence, you need to understand that's what is related with the change of mass flow rate. Okay, let me tell you, like when your engine is running, suppose if I'm talking about say land-based power plant, that will be rotating at constant speed. As per the load demand or load requirement, they will change the rotational speed of say turbine as well as say compressor. But when I'm talking in terms of application, say for aero engines, what is happening? Say when I'm having say takeoff, means from ground it is moving upside, I need to have maximum amount of thrust. And that maximum amount of thrust, that's what is been designed for. Okay, so your aircraft engine, it is designed for maximum thrust condition. So all these components, they are working exactly as per the design condition. But when I am flying at certain altitude, what will happen? Because of change of height, my density is changing, my mass flow rate is changing, and my thrust requirement also will be changing. Because during the cruise condition, my weight force, that's what is being balanced by lift of my aerofoils. Only purpose of my engine is to give forward motion. So that's what I say as off design condition. So you need to understand, when my engine is working under design condition, this is what is my situation. When my engine is working under off design condition, this is what is my situation. Okay. So as I told, this is what is called say performance map of my say compressor. This is somewhere I am having say design condition, and this is what is say my maximum pressure point. Somewhere here I'll be having choking point, that means there is no pressure rise, and maximum mass flow rate condition. This is what is representing my flow condition or flow physics change. As I told, when I'm moving towards say low mass flow rate side, say I'm moving towards the low mass flow rate side, what will happen? My incidence angle, I will be having the separation of my flow on the suction surface. So what it will do, it will try to change the angle of attack for say next coming blade, because this is what is my rotational direction, and this blade, that's what will be changing with decrease of angle of attack. Okay, now particular time I'll be having loading of my aerofoil and unloading of my aerofoil, or say loading of my blade and unloading of my blade. If that's what is your situation, I'll be having repetitive change. If that will be continue, then it may possible that my blade will get failed because of fatigue, because it's a cyclic loading. Okay, now let's see, this is what I want to show. This is what is one of the critical problem when we are talking in terms of say compressor. That's what is said, it is called say compressor stall. Okay, so this is what I was showing. What is happening, suppose if I say this is what is my rotor and this is what is my stator. So when my mass flow rate is changing, that time there may be possibility that in this deep region my flow will get separated like this. When it is getting separated, that's what is making small kind of stall cells. Okay, so let me show you. This is what is making the stall cells. Now what will happen? This is nothing but the low momentum fluid pockets. Dead pockets that will be moving towards say next stage of my compressor. Then it may happen, it will be subjected to form say full stall. Again, that's what is moving downside. That's what will do whole my passage, it will get say occupied with this low momentum fluid, and that's what we name as a surge. Okay, so let me move next. Here this is what is your case. Suppose say if I consider,
Dr. Mistry sir,
yeah, yeah,
can you
okay,
please use that pointer again?
yeah,
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 thank
okay,
you.
okay, yes, yes.
Sorry.
So yeah, so this is what we were talking in terms of having say small pockets. This is what when we say. So if you look at it, says this is what is the line. If I join all the performance map, then this is what is representing my stable condition. So on right hand side what we have, that's what is called stable operating condition, and on left hand side what we have, that's what is called say unstable operating condition. Okay, now when I say when I'll be having disturbance, that's what is of low intensity, then I'll be having this kind of pockets. Let me tell you here. Now when you are flying in aircraft, number of times the pilot used to announce, say we have turbulence, so just tie up your seat belt. Now what you mean by this turbulence, this is nothing but the intensity of my air, that's what is going inside, that's what is changing rapidly. So that is the kind of this pocket. So in particular region I'll be having high mass flow rate, in particular region I'll be having low mass flow rate. What it will do, it will combine together, somewhere it will be making big size pocket. Okay, that's what I say, it is severe and abrupt. Now what will happen? So you will feel whole your aircraft, that's what is having say vibration, heavy vibration. Sometimes you will find the whole your compressor that will go under surge. Surge in the sense what is happening, say your when engine is running under good condition, high pressure and high temperature air that will be entering inside the combustion chamber. Because of presence of say disturbance inside my flow, it may possible I'll be having the blockage of my flow at the exit of my compressor. Now what happens, say upstream side means at the combustion chamber I'm having high pressure and high temperature air, and here I'm having low pressure air. So now my air will try to move in backward direction. So from combustion chamber towards the front side it will come out. Okay, so many accidents that has happened because of this. Okay, so whenever people they are doing design, they always be take care in terms of what we are talking for, say, stall, or what we are talking in terms of surge. So this is what is very critical and very serious situation, very typical situation that will happen when your engine is flying. So if you ask like what is the heart of your aircraft, I say the heart of my aircraft is aero engine. Let you be very good aerodynamist, let you be very good structure engineer, let you be very good in terms of your controls. But until and unless your heart pumps, it is of no use. Okay, now inside the engine also, if your compressor is not working fine, your whole engine is of no use. Okay, and there were many accidents in past that has happened because of this surging. So you can say now our next target, when we say in terms of CFD analysis for turbo machines, we need to identify these stall cells. We need to identify this line when we are doing the design. So this is what is my requirement now when I say I want to do CFD analysis of my compressor. Okay, so let's see. Next is in terms of, say, your transonic flow. If you look at the big size fan what we are having, what is happening if my fan is rotating at particular speed, and if my height or my diameter of the blade it is large, then it may happen this my rotational Mach number, with what I say is empty, that will subject it to, say, supersonic or transonic in that region. Why it is? Because my radius it is changing all the way from here to here, and if my height of the blade is larger, it is subjected to this kind of situation. What will happen if this is what is your situation? Then like your flow near this region, that will be transonic. Okay, so this is what is representing my upstream propagation of my Mach waves or shock waves, and I'll be having expansion fans. Now here, this is what is putting additional challenge in sense of design for, say, compressors. Let's try to understand. If you recall, I was talking to you in terms of, say, aerofoils. So these are the aerofoils what we are using for transonic flow. Here, this is what is representing my double circular arc aerofoil. Okay, so this is also one kind of aerofoil you can use for your compressor. Like you can have your aerofoil conventionally, what you already know. That kind of aerofoil also we are using. This kind of aerofoils also we are using. You need to understand when my flow is transonic, that time I cannot use the conventional aerofoil or C4 aerofoil. What is the reason? Just try to understand. Now this is what is your case. I know my inlet Mach number is, say, it is more than 1.4. Then there will be the shock that will be standing in front of my blade. If my this blade it is, say, blunt blade or, say, circular or elliptical blade, then it will give you bow shock. Okay, that's what is not desirable. In terms of when I say my flow is supersonic flow, always I'll be having those blade and, or what we say, leading edge that need to be sharp, so that my shock that will be standing at that point. Now what is happening? If you go downside, I'll be having the expansion fans, because I'm having my flow or the surface that's what is turning. Okay, so that's what is giving me my supersonic acceleration in that region. And as I know, when my flow is supersonic, it should always be terminated with normal shock. So if you are looking at, this is what is my shock, that's what is standing in front of my blade, that's what is moving towards this blade, and this shock, that's what is, say, m equal to 1. We can say that's what is my normal shock. And downside, if you are looking at, say, here it is, say, Mach number 1.2, here my Mach number is 1. Say 0.8. So my flow now downstream is subsonic flow. My upstream flow is supersonic flow, and my downstream flow is subsonic flow. Just try to understand. Now here in this case, what we know, when I'll be having, say, normal shock, I'll be having great rise of static pressure. What my diffuser is doing or what my compressor is required for, what is my requirement? My requirement is to rise the pressure. So now people, they started using this in terms of benefit. What they say, they will be getting very high static pressure rise by using this shock. And this is what is my conventional or say subsonic diffusion. That's what is happening. If you look at, this is what is having say diffuser say. Now later on people, they realize, they say, okay, let's try to use say high Mach number condition. They are saying like my Mach number condition is say inlet Mach number condition is say 0.6. If that's what is your case, what is happening here, I'll be having my bow shock, that's what is placed here. Okay, and I'll be having my expansion shock. So in this particular region, because of my curvature of the blade, I'll be having say my diffusion, that's what is say supersonic diffusion, and later on because of this terminal shock, I'll be having subsonic diffusion. So you can say if I'm using say double circular arc aerofoil, and when I'm using say multiple circular arc aerofoil, I can achieve very high pressure rise. Okay, even people, they are not satisfied, they say okay, suppose say let's try with say very high Mach number, say most modern compressors, they are having this kind of aerofoil, it is called S-shaped aerofoil. Just look at what flow physics you are getting. I'll be having very large supersonic diffusion and very small subsonic diffusion. Okay, so now the purpose of CFD in case of compressor or say turbomachinery, that is also to develop this kind of spatial aerofoils as per my requirement. Now you need to understand whatever we were discussing up till now, it was subsonic flow. Now I started talking in terms of supersonic or transonic flow. Okay. So let's try to understand, say this is what is my performance map. If you are looking at, this is what is my design condition. So if you look at, when I'll be having my design condition, what is happening, I'll be having that end of the shock, I'll be having normal shock, that's what is placed here, and then I'll be having say my subsonic diffusion. When I'll be talking in terms of say near stall condition or peak pressure condition, what is happening, my shock that will be standing somewhere here, and I'll be having subsonic diffusion. Similarly, if you are talking in terms of choking condition, what is happening, my shock all the way, my terminal shock, that will be happening at the exit. And suppose say if I'm working at high mass flow rate condition, then I'll be having my say shock, that's what is placed in the passage. So you need to understand, as per my change of mass flow rate, as per my requirement of pressure ratio is changing, my shock structure, that's what is moving up and down within the passage. Okay, so this is what is one of the good CFD analysis, that's what was done in order to understand this condition nearly stall. If you can look at, this is what is happening in sense. Now here, if you look at these contours, what these contours are representing, you know, you should not forget, though you are having shocks, your blade surface, it is a solid body, it's always will be having say the chances of say growth of boundary layer. So in this particular region, I'll be having interaction of shock and boundary layer. So people, those who are working in say compressible fluid flow, they can understand now how difficult it is in terms of analyzing this flow physics. Okay, so this is what is one of the challenge to capture this kind of situation. Okay, now let's move. Suppose say, now coming to the next component, say when I say next component, that component is nothing but this is what is my turbine. So compressor, as we discussed, the purpose is to compress the air. The purpose here for the turbine, it is to accelerate my flow. Now when I say I want to accelerate my flow, what combination I'll be having? I'll be having stator. So if you look at carefully, this stator, sometimes people, they are writing that as a nozzle guide vane, and I'll be having rotor. So I'm having stator and rotor. So whatever flow that's what is coming out from my combustion chamber, that will be striking on this nozzle. Now the nozzle, as you can see, my this area, inlet area and my exit area, they are different. So what it will do, it will do the acceleration of my flow. That accelerated flow, that will be striking on my rotor blade, and as I told, because of that my blade will start rotating from pressure side to the suction side. Now you need to understand what we are talking in terms of using the benefit of your lift force. Okay, so this is what is one of the configuration. Here if you look at this particular region, that's what is defined as a HP turbine. So HP turbine blades, if you are looking at that, they are say your shorter blades. It may be of 1 centimeter height or maybe 2 centimeter height, depends on the design. Okay, and if you are moving downside, what you are observing, my blade height, that's what is increasing. It may be say maybe 5 centimeter, 10 centimeter height. I have seen the blade that's what is having say 20 centimeter height. Yes, now you need to understand here what we were discussing in terms of say continuity, what is happening here in the turbine. Say turbine is a device in which your flow is getting accelerated. When I say flow is getting accelerated, you need to understand I'll be having drop of pressure. When I say there is a drop of pressure, that means my density also will be dropped. Now what my continuity says, my inlet mass flow rate and outlet mass flow rate need to be same. If I am making my assumption, say my axial velocity is remains constant, then in order to compensate for reduction in your density, my area need to be increased. And that's the reason why I'm having shorter blade here and I'll be having taller blade here. Now it has its own aerodynamics. Both the blades, that's what is having say special kind of requirements. Let's see. Suppose say this is what is say your HP turbine blade. That's what is fitted with say Rolls-Royce Trent 500 engine. So I'm talking about this blade. Just look at this is what is a blade. It's having say 1.5 centimeter height, and that's what is operating at say 1900K, 1600 degrees centigrade. Okay, now just try to understand what it says. Like HP turbine for this Rolls-Royce engine, that's what is producing 36.5 megawatt of power at the takeoff. You can imagine this power, 36.5. Let me put in other words what it says. This is what is equivalent takeoff power for 25 split fire aircraft Merlin or Griffin engines. So like this, these are the trainer aircrafts. So you with this power you can fly 25 aircrafts. Just imagine. Now what it says, one of the turbine blade, it is having such 70 blades that can produce 700 HP power. Single blade I am talking of. Okay, what it says, which is the power output of your F1 car. Just imagine what is the power that's what will be generated by this turbine, single turbine blade. Okay, and that too, that's what is operating at 700 degree centigrade, more than that of its melting point temperature. So you can understand what amount of heat it is subjected to. Okay, and you know it is subjected to gravitational load of 60,000 G at the time of takeoff. Oh, so just look at this blade. If you are looking at, this is what is having some spatial shape, and if you look at carefully, that's what is having say holes on the surface. This is what is say my leading edge, here it is my trailing edge, and this is what is my nozzle blade. Now this nozzle blade, as I told, that's what is subjected to flow, that's what is coming out from my combustor. So it will be striking here. When it is striking on my nozzle, there are chances that my blade will get melt. So in order to avoid that, we need to provide certain kind of cooling. Now when I say cooling, you need to understand, the question need to start in your mind. I need to use my CFD analysis for designing this cooling blade, or to design the blades for this cooling. We will see this. Okay. Now let's see like what we were discussing in terms of my CP distribution for, say, this is what blade I am having for, say, turbine. Again, for turbine I'll be having, say, leading edge and trailing edge. I'll be having suction surface and pressure surface. Now you need to understand the pressure P1, that's what is higher, my pressure P2, that's what is lower. So you can say the exit pressure is lower. We can say my flow, it is working under favorable pressure gradient. When I say my flow is working under favorable pressure gradient, the chances for my flow to get separated, they are less. What is the meaning of that? That I can give more camber to this aerofoil. I can turn, I can bend more. If I'll be saying I can bend more, I'll be having my CP distribution accordingly large. Just look at. So in order to represent, do not get confused with the same. This is what is representing my suction surface and this is pressure surface. Just look at. In order to represent, say, conventionally for years, people, they are using CP distribution for turbine, saying like negative axis they are putting on reverse way. Okay, here also near this condition you can understand, say on my pressure surface I'll be having, say, initial acceleration of my flow, and then after my flow, that's what is almost remains constant on concave surface. Similarly, what is happening, I'll be having my acceleration of flow up to certain distance, and that's what is getting decelerated. Okay, so this is what is representing my CP distribution for turbine blade. Now when you compare this CP distribution, you can imagine by scale, this is what is greater than that of the area what we have observed for the compressor. What is the reason? Because I need to extract more amount of work from my turbine. Okay, and that's the reason why we are having this kind of CP distribution. Now let's see what all are the aerofoils. If you look at, these are the conventional aerofoil, that's what has been defined by, say, NASA. Okay, just look at, this is what is, say, aerofoil, that's what is having, say, larger leading edge radius and small trailing edge radius. If you are looking at this B1, E1, I1, if you look at my area, my curvature for the leading edge, it is smaller. Somewhere I'll be having maximum thickness. Here I'm having maximum thickness. Okay, so let's try to understand what is happening in terms of, say, your thickness. So here if you look at these two aerofoils, that's what is having same thickness, but my camber angle, that's what is different. So it says 65 and 80 degree. If you are looking at, if I'll be changing my thickness, say thickness to chord ratio, that's what is, say, it is 15. Here it is 15. This is what is. Okay, and here this is what is representing my impulse blade. Okay, now when we are talking in terms of this blade, let me share you whatever profiles I have shown. These all profiles, they are the proprietary thing by those aircraft engine manufacturing companies or maybe power plant manufacturing companies. What is the reason? They are spending a lot of money, whole lot of money for research and development. And those research and development activity, that's what they are using for their engine. So they cannot put everything in open domain. Okay, every year, say if you are looking for, say, engine companies, say GE, Rolls-Royce, Pratt & Whitney, Siemens, Honeywell, maybe say Snecma, all these companies, they are patenting number of aerofoils every year. And those aerofoils, they are the proprietary thing for them, and that's what they will not be putting in open domain. Suppose, say, if you are talking for me, suppose, say, I want to work for, say, engine, say I want to develop compressor or I want to develop my turbine, then I need to start from scratch. Okay, these are some of the common or conventionally available aerofoils in open literature. Okay, so initially I need to start working with this kind of aerofoils, and then after I need to tailor my aerofoil. Tailor my aerofoil in the sense I need to modify my aerofoil. Later on, if it is working fine as per my requirement, I can give my name to that aerofoil. That's what the companies are doing. Okay, so you need to be very careful. One of the use of your CFD analysis, that is also for the development of this kind of aerofoils. So here you can look at, this is what is a subsonic inlet, and I'll be having shock that will be standing here. So that's what is representing my choking condition, and my exit will be supersonic. Here this is what is, say, supersonic inlet, supersonic exit. This is what is a cut section at the tip for steam turbine. That's what is supersonic inlet and supersonic outlet. Now just look at, as I told, you can modify your aerofoil as per the requirement. This is what is, say, the profile, vent profile. That's what they have used for energy efficient engine. That's what was a project run by, say, US government in collaboration with GE and Pratt & Whitney. They have developed their own aerofoil. This is what is, say, nozzle aerofoil. You can look at what is the shape of my leading edge, where is my maximum thickness, and what is the shape of my trailing edge. Just look at, this is what is representing my CP distribution. So you can understand this is what is the expected CP distribution. Similarly, this is what is for, say, my rotor blade. Just look at, I'll be having maximum thickness somewhere placed here. So I'll be having, say, on my pressure surface and suction surface, I'll be having my acceleration of flow, and then after whole deceleration, that's what is happening here. Okay, so this is what is representing my CP distribution. Similarly, this is what is a profile they have used for, say, advanced turboprop drive. That's what was for space application. Just look at the aerofoils. Okay, now there is one more trend, that's what is going on for last 10 years. So what was the earlier case? People, they were using, say, experimental results. Say NASA, they are having very good wind tunnel facility, cascade tunnel facility. So based on that, they made a whole lot of aerofoils, and they are having the data. They are having CP distribution. And based on the requirement, they are collecting those aerofoils and they are putting that aerofoil as per their requirement. Now the new trend has come. What it says, rather knowing this aerofoil, let me know what is the amount of work I am expecting, or CP distribution, that's what is known to me, and I need to design the aerofoil. That's what is called inverse design problem. We will discuss that also in the next session. Okay, so like day by day, as per the requirement, as I'm telling, the expectations, that's what is changing, and people, they are looking for more and more opportunities in sense of development. Okay. Now in terms of, say, losses for, say, turbine passage, let me straightway move here. What it says, I'll be having different kinds of losses. Let me go to the next slide. Okay, next slide. This is what is the flow passage between your turbine blades. Okay, now here you need to understand, as I told, I'll be having, say, blunt leading edge. That's what is present here. Okay, what I need to do, you need to understand, for my compressor aerofoil, I need to have some acceleration of flow and then after deceleration. But in the case of turbine, I'm looking for whole deceleration. That's what need to be happen on my suction surface. So this is what is a curvature for me. Now what is happening, say, this is what is a solid body. So this blade, it is been placed on my hub where I'll be having solid body. This blade itself, it is a solid body. So what will happen, I'll be having my growth of boundary layer all the way from inlet towards the blade. Okay, so that's what is representing my growth of boundary layer. When it is coming in contact with this, it is making this kind of, say, point, what we say as a saddle point. Okay, so this is also one kind of fluid mechanics. Maybe people, they are not teaching in the courses. When you are teaching or when you are studying or when you are reading, say, CFD analysis, I used to say number of times to my students also, even my end users also, that you need to understand the flow physics. And in order to understand the flow physics, you need to have very good understanding in terms of post-processing. What all you need to post-process or what all you need to plot. Okay, so this is what is representing the vortex that will be formed here. This is what is having, say, it is called horseshoe vortex. So when I am having, say, blunt body, that's what is placed inside my flow, then from some distance I'll be having the formation of horseshoe vortex. So this is what is representing my horseshoe vortex. So when this horseshoe vortex, that's what is moving on suction side, it is called, say, suction side horseshoe vortex. I'll be having other split, that's what is moving, say, pressure side horseshoe vortex. Okay, so if you are looking at, this is what is representing, say, cut section. It is in sense at this location. Now what is happening between the passage, I am having, say, high pressure surface and I am having, say, low pressure surface. Now what is happening, my flow always will try to move from high pressure side to low pressure side because of gradient, pressure gradient. So what it will do, it will try to deflect this vortex towards the surface. So it is moving towards my suction surface. So just look at, this is what is moving towards my suction surface. Okay. Now, because I'm having solid body and I have curvature, there is a possibility I will be having, say, corner vortex. So this is what is representing my corner vortex. That's what is formed on suction surface as well as on, say, my pressure surface. Okay. Now, like I'll be having this horseshoe vortex. That's what is coming from my suction surface, and that's what is coming from my pressure surface. They all together, that's what is making the big size vortex. That's what will be coming out from my blade. Okay. Now, as I told, along the blade, I'll be having the differential pressure and I have the growth of boundary layer. And that's what is giving me, say, wall induced vortex. So this green color, if you're looking at, that's what is showing my wall induced vortex. So at the exit, I'll be having contra rotating vortex that will be coming out. Okay, so the use of CFD, you need to understand, I need to capture this physics. What it says. Now, when I say this is what is coming out as a vortex, we can say that's nothing but it's a low momentum fluid. And when it is low momentum fluid, that's what is decreasing what work I'm expecting in terms of for that device. Okay, so a lot of research and development activity, that's what is going on for, say, minimizing this secondary loss. It says maybe skewed or swept blade profiling, modification of leading edge near the end wall, non-axis symmetric wall profiling. If you start Googling, you will understand how people, they are improving the efficiency of the turbine or improving the efficiency of the compressor by minimizing these losses. Okay. Now all these things, that's what is influenced by other parameters also. It is not like it is single condition. That's what has been affected by your incidence angle. It is also been affected by your flow turning angle, your solidity, aspect ratio, blade loading, inlet vortex intensity. All this together, whole your physics, that will get more complex. Okay. Now we just try to understand here. This is what is the overall picture. As I told, I'll be having, say, my flow to be accelerating flow. So here you can look at this particular region where I'll be having my flow to be transonic. So again, this incompressible flow or incompressibility effect, that's what is making whole my physics more complex. Just look at. So this is what is my nozzle and this is what is my rotor, and how my wake, that's what is moving, how my shock, that will be interacting here. I'm having animation, I will show that animation form. And what we do next, it is in terms of, say, my tip clearance flow. Here also, you need to maintain certain amount of tip clearance. Let me share here, when I'm talking in terms of turbine, what is happening, because it is subjected to high temperature, I'll be having thermal expansion of blade as well as casing. So if I'll not be giving sufficient amount of clearance, it may possible that my blade will get stuck up with the casing and it will stop rotation of my wheel, and that's a gone case. So mechanical requirement, it is you must have the clearance in between casing as well as between the rotor. One more thing is, like in earlier case, what was happening for the compressor? My flow rotation, it is from suction side to the pressure side. Okay, and my jump of say my leakage flow, it is from pressure side to suction side. So I was having say cross flow kind of configuration. Now here in this case, what is happening? My flow is jumping from pressure side to suction side, and my rotation is also from pressure side to suction side. So that's what is making, it makes like my flow to be little complex in the tip region. Okay, so in tip region you will be finding there will be separation bubble that will form near your say pressure surface what we are having, and that's what is giving you jet kind of idea here. It is decreasing somewhere, I'll be having mixing, and that's what will give your tip leakage vortex. Now in this case, I am having growth of boundary layer because of this end wall, growth of boundary layer because of this blade, and I am having this end wall flow. I am having the secondary flow. That's what is coming out from the passage. All together, that's what is making whole my flow within that passage as highly three-dimensional flow. Okay, so we need to be very careful. There are people, they are using some kind of mechanism with which they are trying to minimize the losses. That's what is happening in say end wall region. Now this is what is say when the engine was flying, say for your Rolls-Royce engine, they found like when they are doing the Reynolds number calculation, they are finding in this particular region we are having the Reynolds number, engine Reynolds number, that's what is decreasing. Now the situation is, it is little difficult for you at this moment to understand, but you can understand when I'm having say my flow to be low Reynolds number flow, I'll be having all kind of complexity because of flow laminarization. Okay, so this is what is one of the section for my high aspect ratio blade or my LP turbine blade. You can see, because of my Reynolds number, that's what is changing. I'll be finding my flow separation, that's what is happening. Though I say there are less chances for the flow separation to happen in my turbine blade, but because of change of my Reynolds number, I'll be having, this is what is say, you have flow separation. Because this blade is a taller blade, I'll be having secondary flow. That's what will be extended up to 30% of my hub and 30% of my shroud. Okay. Now, like when we are talking in terms of turbo machinery flow, what all I was talking is, the complexity, that's what is happening. This complexity is because of secondary flow caused by viscosity, your complex geometry. You will be having say passage vortex, leakage vortex, corner vortex, trailing edge vortex, horseshoe vortex, scraping vortex, all together along with the rotation that will make your flow to be very complex. Same time, what is happening, your rotor is rotating and your stator is stationary. Because of that, it will give the unsteadiness in the flow. Okay, that's what is making even this case worst. Okay, the pattern near the near wall region, what we say laminar flow, transition flow or turbulent flow, along with this separated flow, it is creating more trouble. And the problem, that's what is not ending there. I can have my flow to be say incompressible, subsonic, transonic or supersonic. So that's what is putting additional complexity. Now what will have say when I am talking in terms of say hot section, say for turbine, what will happen? I am using my cooling of blade, and for the cooling of blade I need to have air injection in that. So you can understand how the complexity that will be happening inside my flow passage. Okay, so let's see, this is what is representing my wake transportation, what we say. Okay, now let's see, let me look at the time. If Professor Sonavane, he will say, then so, sir, we can have the break
we
for.
may have a break of 15 minutes. You can
Okay,
have
okay,
a
fine.
water and tea so that
Yeah, fine.
you also see long time.
Yeah, okay, okay, fine, fine.
Is that okay?
Yeah, fine, fine, Will. So I'll be joining
So
again.
you may have a please a tea or something like that,
Okay, okay, fine, fine.
and then
So
again we will start sharp at 11:15.
okay, okay, fine, fine, sir. Yeah,
Okay.
I
So
hope.
participant, please do not leave the team. You can also have a tea or coffee in the cafeteria, and please come back quickly so that we will start at 11:15 sharp.
Okay.
If you are here, we can have a together tea. Dr. Mistry.
It's okay, okay.
but, but the time have come such that
Yeah, yeah. I can understand.
yeah, yeah. Very nice session, sir.
Yeah, fine. Thank you very much. Yeah, so let's
You
see.
can have
Like
some water
next session,
because
that will be more in
you
terms
can
of.
have some water and a coffee, something like that, so that we can talk. Otherwise, again, I will consume your time while talking.
Okay, okay, no problem. Fine, fine, sir. Yeah,
Okay.
yeah, join you again. Yeah.
Yes, yes, yes. 11:15.
Yeah, Professor, so can we start with now?
Yes, sir. Yes, sir. Waiting for you only.
Yeah, fine, fine. So let's see. So this is one of the animation video that's we got from say TU Gres. That's what we'll discuss what we were talking in terms of complexity of flow physics. Just have a look at. So this is what is transient 3D Navier-Stokes equation solver. Some of their experimentation with PIV and LDV. Just look at midsection. These are the vorticities. That's what is present. You can see like how my vortices, they are moving in between the passage. This is what is representing what we were discussing in terms of say my tip clearance flow from that rotor part. And in between passage also what we can see, these are the flow structures which are moving within the passage.
Professor, these are the velocity distributions?
Yeah.
Yeah.
So this mainly iso surface. That's what is representing your static enthalpy. That means in sense it says losses. Okay, so this is what is stator, rotor and stator combination, and that's what is representing my entropy. So this is what all we are looking for in sense. This is what is for one stage, and such 4 or 5 stages we are having for turbine, and maybe 10 or 12 stages we have for compressor. This is what is the requirement when we say in terms of say aero engine application. So if you look at, this is what it was showing in terms of what all complexity we are having. It says like unsteadiness, that's what is mainly been present when we are talking in terms of say turbine or compressor. It is potential interaction. Then we will be having say vorticity. We can have shock wave interaction. We can have hot streak. When we are talking in terms of say inlet at the nozzle and at the exit of nozzle and at the entry of rotor, you will be having those high temperature gas. That's what is flowing. That's what is having say uneven distribution of your temperature. It may be having non-deterministic. That's what we cannot predict or we cannot like find with our conventional way. That's what is say tip leakage flow, shroud flow, coolant injection, say shear layer flow. That's what is wake and secondary vortices. There's turbulence. We have no idea of like what is the turbulence intensity of my flow, the growth of boundary layer. So all these things, that's what is making my flow through turbo machines. When I'm talking in terms of say compressors or turbine, that's what is making my flow physics very complex. Okay. Now let's say like this is what all we were discussing of. Then what are the challenges? Challenges, that's what is when we are talking in terms of say CFD. Very first thing what we need to understand is CFD is not colorful display. That's what is a computational fluid dynamics. In sense, we need to solve our particular equations, what we say mass conservation, momentum conservation, energy conservation, your ideal gas equation, maybe species, all those things. And you need to solve those equations in small volumes. Okay, so that means when I say the challenges, it says the grid generation for the complex geometry, what we have, rotating domain. You will be having flow, that's what is highly unsteady, rotating, turbulent, capturing of these losses and other viscous effect, turbulence modeling, fluid structure interaction, all those things, they are the major challenges for in turbomachinery CFD. So if you say like in terms of main challenge, the main challenge, that's what is with your aerofoil section. That's what we are using for compressor as well as turbine. You can see all these are the unsolved problem with us when I'm talking only in terms of aerofoils. So this aerofoil that will be subjected to all this kind of complexity. And when I say this all kind of complexity, that's what is making my flow physics very typical, very difficult. And that's what we are expected to do using computational fluid dynamics. Okay. Now let's move it. Say this is what is representing like the growth of efficiency in terms of why SNECMA. It says like initially they were using potential flow theory, then slowly moved towards say 3D Euler, Navier-Stokes equation, now Navier-Stokes. It says over the year they have increased their efficiency. Now if you look at these are the generation of your G engine fan blades. Just look at earlier it was having shrouded blade. Now it is a wide chord blade. Just look at now this engine, that's what is having say reduced the number of blade. Let me share you this blade, that's what is having height around 5 feet 6 feet, and one blade that's what is costing in terms of lakhs of rupees, and that's what is made up of composite material. Just look at the shape, you know, like all these shapes what you are looking at for this blade, maybe for Rolls-Royce blade, even for say G blades, you need to say thank you to CFD. This is what is all possible with your computational tool. We will see how exactly people they are understanding and how they are using this as a tool for the designing. Okay. Now, when I say in terms of say engine development, so for engine manufacturing companies, this is what is a flow chart, that's what they are following with. And here in this case, your CFD, that's what is coming into the picture, what we say in terms of component design. But you know, like until and unless you will be having say testing, this what we are doing in terms of CFD, that's what is not acceptable. So you can say initially you will be given some mission, so specific aircraft application we have, maybe military aircraft, maybe commercial aircraft. You need to do your cycle analysis, you need to determine or you need to select different parameters, then you need to check with their performance based on number of components, you need to check with the weight, you need to do scaling, you need to check with say different component design. So that's where we are using our tool, that's what is named as a CFD. And finally it will go for say manufacturing process, and then after it will go for testing, and once testing is done, then that's what will be used or it will be in use. You know, like it is not like one engine you are making and that engine once it will get certified, all engines will go through. All engines you need to certify. Okay, let me share the experience what was with say Indigo part what we are looking for. So if you read carefully, like for last full years, just it start from January to say March, what was happening say for Indigo aircraft when they are taking off, after certain time or after certain flight, they are coming back and saying like engine is having trouble. Now, when we say engine is having trouble, you need to understand there is something wrong. That's what was done by the engineers and mainly with the designers. You know, in order to do optimization, in order to go for efficiency, people they are using these tools, maybe CFD tool or FEM tool or maybe computational tool. And based on the results what we are getting, if we are going for the development of product, then that kind of situation always will happen. So you need to be very careful. Whatever you design, that need to go through for the testing. Okay. Now let's see, like this is how my CFD that has grown for say gas turbine industries. That's what has started in 60s, as I told. Like the CFD, it is new to us, maybe to many of us, maybe what we understand is after 90s that has come, but no, this CFD analysis that has started in 60s. Okay, for the engine development, those days they were using that for 1D analysis, then they were moving with say 2D analysis, then they went with say quasi 3D analysis, now they are talking in terms of 3D analysis, now we are talking in terms of say unsteady analysis. So this is what is the growth of my development of CFD for say gas turbine engine application. These are some of the lines. That's what is a database with the engine manufacturing company. They are having all this kind of tools. It is not like single person is working and doing something and he's suggesting and that's what is accepted. It's not like that. They are already having whole lot of data. That's what is available with them. They are having their in-house tools. They are not using this commercial package because they need to design, they need to analyze, and with that analysis they need to develop, say, testing rotor or testing stator. Then after they need to go for testing. Once it is working fine, it is okay. If it is not meeting with the requirement, again they need to go for modification in the design, and that's what is whole possible with this database. When we are talking in terms of, say, various CFD analysis, we can say we can have potential flow solution. It is the easiest way. We can have, say, 2D Navier-Stokes solution. We can have 3D Navier-Stokes equation. We can have RANs. We can have unsteady RANs. Let me share you here in this case for the RANs. What we are doing is it is a truncated form of your Navier-Stokes equation with certain approximations. So when we say we are having certain approximation, that means it has that constraint. It has a limitation. People, they started talking in terms of using, say, LES. Now people, they started talking in terms of DNS. When we say DNS, that's what is solving your original form of a Navier-Stokes equation. It does not require turbulence modeling. That's what is giving more accurate solution. But the number of nodes required, it says, like, that's what is in function of your Reynolds number. And that's what is, it says, like, approximately in terms of square of your Reynolds number. So when I say my Reynolds number is 2 into 10 to the power 5, and you need to square that, that's what is the requirement of number of node, and that's what is a constraint. But yes, slowly we are moving towards the direction, say, people started using this LES part for small. Today only I will show you one of the animation that was done with, say, LES, and people, they are working for DNS too, but the expectations and requirements are different. The approaches, it says 2D, quasi 3D, say 3D. 3D, that means what we are doing at this moment, that's what is called 3D. So, okay. And now the analysis, what we are writing is, say, stationary analysis and transient analysis. So stationary analysis, what we say, it is most common and people, they are using for the initial designing. When we are talking in terms of, say, analyzing the developed component, then we need to go with the transient analysis. That will give you minute details of whole flow physics, and it will give the opportunity to modify the design as per the requirement. So this is what is a recent trend. Say you are having 3D, transient and stationary kind of analysis. Okay. So as I told, we need to go with the basic governing equations. It need to solve, your CFD need to solve, say, conservation of momentum, say, energy conservation, equation of state. If you will be having reacting flow, then you need to go with species conservation. Okay. Now, when we are talking in terms of doing CFD analysis, very first step, it is to setting up the domain. So you can say this is what is my axial flow fan, and this is what is, say, my centrifugal compressor. So I need to initially make my domain, flow domain. Okay. Then I need to discretize this flow domain in space as well as time. When we are talking in terms of, say, unsteady analysis, then I need to do discretization in terms of time. I need to define boundary conditions. I need to solve the appropriate governing equation for the domain for this discretized point. And then after, I need to go with the post-processing and analysis of what results we are getting. And this is what we say in terms of CFD to be done. It seems very simple in that sense. Okay, but slowly you will realize, this is what is very big work that you need to understand. Now, suppose if I say in terms of making of domain, that means you need to have your blade profile, you need to have your blade. Okay, for that blade, you need to have all your dimensions. So what you need to do, you need to make your flow domain. Then I need to divide that into number of small volumes. That's what is called, say, discretization. So this discretization, that's also not easy task when we are talking in terms of having curvature like this. Many of you may be aware of what we say in terms of meshing. So meshing is the most challenging part. When you say, like, if I ask my students to do meshing, they will say it's an easy task. You just run the software and make your mesh ready with. It is not that simple. You need to understand. Okay, so discretization itself is art. You know, many people, they are doing, say, the meshing of particular domain in, say, maybe 2-3 hours. Many people, they are spending, say, one day. Many people I have seen, they are spending 5-6 days only for doing the discretization, only for doing the meshing, because they know what they want. Just listen me carefully what I mean to say. They know what they want, in sense, what all complexity what we have studied, the engineer who is doing discretization, he know I want to capture this physics. So whatever losses, whatever say vortices, all those things what we have discussed, that need to be captured. So if the discretization it is not in proper way, then it may not be captured. And after capturing, you need to solve the equations. So there are different people, they used to say they are doing coding. Okay, they are solving basically all these fundamental equations and try to give the solution for that. And after having the solution, you need to do post processing of the results. That's what is very tough part. If you ask me what is tough in CFD, I say I don't know coding, so I say I don't bother of. If you say discretization, I say I will be using my commercial tool, so I don't bother of. Suppose if you say in terms of solving, as I told, I'm not knowing the coding, I will not use my code. I will be going with what commercially available is. Okay, but after doing all these things, I must understand what is my expectation, what I want to do. And if I understand what I want to do, accordingly I need to do the post processing. So very tough part, as I say, is the post processing part. Now in terms of, say, meshing, many of you may be aware of, so I'll not be taking much time in this all aspects. You know what is called, say, structure mesh, unstructured mesh. If you look at, this is what is representing my structure mesh, this is what is representing my unstructured mesh. So this is also unstructured mesh. Okay, it is, that's what I was saying, like, you need to understand what is your requirement. Okay, now when we are talking in terms of analyzing our blade, we need to do discretization. If you are looking at, say, this is what is my blade, now this is what is representing my meshing. Okay, or the volume I am dividing into small components. Just you need to have look at my main interest of flow physics, it is near wall, near the blade wall, what is happening. If you look at here, near the tip region, what is happening, so you can understand what I mean to say and what exactly I am doing. Now suppose this is what is my leading edge. I know at leading edge my blade angle or my flow angle, that's what is changing. So I need to capture that in detail. Similarly, what we are talking in terms of trailing edge, I need to capture the wake, that's what is coming out. Okay, so for that purpose, there are certain topologies what we need to use. Okay, that topology is nothing but it is representing your passage block or, say, blade blocks. Okay, say, let me move here. Say we are having, say, different kinds of meshing. Say I can use O grid. It says like around the blade I need to capture the growth of boundary layer, and for that I need to take care of my Y plus value. Now since this is what is advanced course, so I'll not be spending time here for discussing Y plus. You can understand. Now you know I'll be having my curvature of blade near the leading edge and trailing edge, where I'll be using, say, J grid kind of thing. And in remaining passage, if you look at all this passage where I'm having that passage, I'm writing as a H grid. If I'll be talking in terms of upstream and downstream condition, if they both are not same, they are not same to same, then we can use L grid, we can use C grid kind of thing, you know. So the thing is, the flow physics, what you need to capture around the blade, near leading edge, near trailing edge, and in between the passage, that's what will decide like what exactly you need to use. Okay, so many times people used to ask what results you are presenting. They will say, have you done grid independent study? Or they will ask like, is it grid insensitive results? Because with coarse grid or fine grid, it may happen your result may vary. Okay, in terms, suppose if I say about the compressor, what will happen? With one kind of grading, I will be getting pressurized say 1.2, and with other kind of grading it may possible I may get 1.25 or 1.3. So you should not get happy that I have designed my rotor for say or my stage for 1.2 pressure ratio and I'm getting 1.3. It never happens. Okay, so you need to be very careful. You need to do grid independent study. What you need to do is you need to increase the number of elements and you need to decrease the number of elements with your standard case and just check with for some parameter, performance parameter. If it is coming consistent, you can say now with increase of elements or decrease of elements my results will not change. That's what is called say your grid independent study. Now if you look at here, this is what we need to understand. So earlier, let me go back here. So, when I say I want to analyze my rotor and stator combination, so you can understand, suppose say I'll be having my rotor diameter of say 2 meter. Okay. And I'll be having say 20 blades or 18 blades. And if I'll be analyzing that kind of physics, then I need to have very high computational power. I need to have very good meshing tool. And that too, if you look at say even for commercial package, people they are limited with number of elements. So what you need to do is you need to take only one blade. Just look at here, this is what they have done. They have selected only one blade. So this is what is my inlet here, this is what is my outlet. And if you look at this surface, what they are writing as say periodic surface. Periodic in the sense whatever is effect here or data what we are calculating here, that will be transferred to the next rotor. Same way here what we are calculating, that will transfer here. Similarly, if you are looking for say centrifugal compressor, we can say this is what is my blade, single blade, since it is having splitter blade. So I'm selecting two blades, inlet, outlet, and I'll be having periodic surface. So let's move to that slide here. Just look at. So this is what is my inlet, outlet, and this is what is representing my periodic surface. Upper side, that's what people used to say shroud or say casing, and on blades when we are installing on the surface or disc, that's what is called hub. Similarly, this is what is for say radial machine. Now, very important case, that's what is what boundary conditions to be used. Okay, now depends on application, you need to decide. Suppose what you are solving, whether your flow through that passage is say compressible or incompressible. Okay, when I say I can use say total pressure, total temperature, velocity profile, that's what is very common. There are other kind of boundary condition, we can say velocity inlet, mass flow inlet. They are not much common. They are having certain limitations, and that's the reason why we are not using that. So most common idea is to use total pressure inlet condition. Or maybe if you are having say experimental result in which you have measured your velocity throughout your blade, you can put that as your boundary condition. Now in terms of exit condition, static pressure, that's what is conventionally people they are putting. Okay, many times people they are using say mass flow outlet condition also. Let me tell you, when you are analyzing the compressor, you need to have capture of certain flow physics and detailed study what it says, what it recommends based on experience. It is preferred that you use static pressure outlet boundary condition. Okay, now that's what say for compressible flow, it says static pressure outlet boundary condition, that will give you the better results. Now surface, you need to understand the surface we are considering as viscous effect. That means I need to put no slip condition and adiabatic wall. When I'm analyzing say turbine kind of case, that time I need to consider say boundary condition as constant heat flux condition. Okay, now periodicity what I was talking, it is based on like blade what we are using. So I can say half the pitch of my suction side, half the pitch of my say pressure side. That's what we are considering as a domain. Now what we know, my rotor, that's what is rotating. Physically we need to understand what I want to analyze. Say I want to analyze stage, that's what is comprising of rotor and stator. When I say rotor, it is rotating. When I say stator, it is a stationary part. So what I need to do, I need to connect the stator and rotor. When I say I want to connect one mesh, that's what need to be rotating mesh, and other mesh what is say stationary mesh. So I need to connect these two. When I'm talking in terms of say experiment, say if you ask me like what detail you have in terms of CFD, I say I have limited because I'm experimentalist. I'm more interested in doing the experiments, but I will show you being experiment, still I'll be having say use of this CFD. So what I need to do is I need to put the interface between the stator and rotor. Let's see what is that. So here if you look at, this is what is my one fluid domain, this is what is my other fluid domain, and in between if you are looking at, this is what is called interface. And for that interface we are having different approaches. One approach, that's what is called say mixing plane approach. So what this mixing plane approach is doing, it is doing averaging in the circumferential plane. So here if you look at in this plane, they are doing circumferential averaging, and that say like uniform flow that will be going downside. Okay, so this is what is say mixing plane approach. It is doing circumferential average both near the inlet and at the outlet domain, and thereafter at the exit it is giving uniform flow. Now when I want to capture my flow physics in terms of what wake, that's what is coming out from my rotor or stator, and what is the effect on say downstream, that's what is difficult to capture. Okay, so what it says, the limitation for this approach, it is it removes the impact of secondary flow and flow separation, and that will not give what exact flow physics we are looking for. Okay, now this is what was the approach proposed by Denton long back in the 80s. That time that technology in terms of coding, technology in terms of computation, that was not that mature. Second option for people what they are adopted with is you should not have averaging at the plane. That's what is called a frozen rotor approach. So whatever data, that's what is coming out from your rotor or stator, the same data need to be transferred downstream, and that's what is called say your frozen rotor approach. But here in this case you need to be careful. Say when I'm having say 20 number of rotors and 20 number of stators, then 1-to-1 matching in terms of pitch is possible. I will show that in next slide. Okay, but I know my number of stators and rotors, they are different. If that's what is your case, then you need to check with the motion of your stator and rotor, and then you need to capture the physics. Let me show you. Say this is what is. Say this is what is work by one of my PhD student. Okay, so here if you look at, we are having say tandem bladed rotor. This is what is my stator. What is happening if you look at, it says this is what it is doing in terms of averaging at this plane, and that average flow value, that's what is getting transferred. So what physics, what wake, that's what is moving here, that's what is not been captured. Similarly here if you look at, say this is what is representing the effect of your rotor wake. You can see what we have. Okay, now as I told, you need to be little careful. Just look at, you are having say some kind of discontinuity in that sense. This is because of what we say in terms of pitch position. So that's what is called clocking effect. Okay, so you need to be little careful in terms of capturing this physics. So you need to put the clocking effect. So you need to play with shifting your angular shift of maybe rotor or maybe stator. And this is what is giving the actual flow physics. Let me tell you, like when we used to attend the conference students or say scholars, they are coming and presenting the results. Then they are using this concept. If you ask why you have used this concept, they will say, sir, expected pressure rise we have got only with stage, we have not got with the frozen rotor. That's what is showing, like the understanding in terms of these approaches, that's what is not clearly been done. So you need to be very careful what you are looking for. Okay, now let's move. Next question that will come, that's what is with the selection of your turbulence model. Okay, so there are different models available. There is no fixed model, that's what we can say you can use for all kind of simulations. People used to say like the Baldwin-Lomax model. Sometimes people used to say one equation model, Spaldra-Almaraz model. They are very good in terms of capturing the physics, but like it is sometimes it is giving the unphysical results, and that's the reason why this is what is not been accepted. What we can say, it is not exactly capturing the physics in terms of separating flow, rotating flow, flow with say strong effect of secondary flow. That's what we cannot do by using this kind of turbulence models. Okay, that means now we need to have strong turbulence model, that's what will capture the whole physics. Otherwise it is no use. Why we are doing our CFD analysis? If the physics we cannot capture, it is of no use. Okay, and for that purpose, people they started using say K epsilon model and what we say K omega model. Now with this K epsilon model, what it says, it is over predicting your turbulence flow. And that's the reason why when we are having say acceleration and deceleration of flow, that's what is happening near the leading edge or around your shock, that cannot be clearly captured when I'm using say K epsilon model. Let me tell you, if conventionally if you are asked someone what is the use of, so they used to say in order to analyze say free stream condition kind of flow or unconstrained flow, you are using K epsilon model. Now here in this case my flow is constrained between the passage. That means I cannot straightway use this K epsilon model. And that's the reason why Mentor he has proposed K epsilon model. And it says it is capturing the physics nicely in terms of flow with say separation under adverse pressure gradient. One more thing is it is also calculating Reynolds stresses, and that's what is because of Coriolis component. Okay, so if I take elemental part between the passage, it is having rotation as well as sliding, and that's what is very important to capture when we are talking in terms of turbo machines. And that's the reason why this K epsilon SST model, that's what is most widely been used. Okay, now in terms what is our requirement in terms of selection of say your solver, what all we want to capture is say different fluid flow properties. And in order to calculate that, what we need to do, we need to go with say solving Navier-Stokes equation. Okay, now there are flow non-uniformity, that's what is coming, what we are defining as convective term. And that convective terms, they are because of maybe turbulence or because of say density variation, because we have shock waves. So in terms of solvers, what we know is we are having two kinds of solver. One it is a pressure based solver or pressure correction method. Second, that's what is a density based solver or say time marching method. Conventionally, we are using this density based solver. Standard approach, it is been used for say compressible flow, and pressure based, that's what we are using for say incompressible flow. But still, people used to say, no, I want to use this density based solver for my incompressible flow. Yes, that is also possible. What you need to do, you need to have say time derivative of density in your continuity equation, that will get disappeared, and you need to have preconditioning method to be adopted in order to solve your compressible code or say density based code for solution of incompressible flow. Similarly, this pressure based also you can do. You need to have say compressibility extension need to be adopted. So now when you are solving that, say even in commercial package also, if you are looking for say, people used to say I'm using Fluent for my solver. People used to say I'm using ANSYS. People say I'm using star CCM. Yeah, there are many solvers, they are available. What we say software. So what kind of software you are using for what kind of flow physics, you need to be very careful. And over the year, with maturity of technology and with strong database of experimental results, now companies, they are having their own code because they have understood what kind of flow physics they are looking for and what kind of flow will be there between the blade passage. Okay, so that's what, this all what we are talking of, that's what has grown over the year. Now, in terms of say convergence criteria, so like we, we used to say like my solution need to converge. So what we are doing is we are putting some observation parameter and we are finding the residuals, and based on that we are saying your results are converged. But there are different possibilities, say without resolve wall condition or with resolve wall condition. You need to take different approaches, and more complex situation will happen when I'll be having say heat transfer simulations. What is say when I'll be simulating this heat transfer, my aerodynamic field that will get converged, but my thermal field will not get converged. What we are talking in terms of density, or what we are talking in terms of heat transfer, or what we are talking in terms of say temperature. So under that condition, what it says, you need to stop your run, then you need to check with the parameter. If it is working fine, it's okay. Okay, so very well resolve wall and heat transfer, it can take sometimes 10 times longer for the thermal field to get converged. Now, when we are talking in terms of application of turbines, you can understand what complexity we are having. We are talking of aerofoil. That aerofoil is having aerodynamic property. We are talking of hot gas, that's what is having thermal property. We are talking of cooling, where I am having cool air. So, like that's what is a big issue with. Now, if you ask, sir, what all are the packages, that's what is available. So you can say for analysis, I can have ANSYS, I can have MySys, I can have Fluent, Star CD, Vista, APNASA, Fine Turbo, CF Turbo, OpenForm. It is also now growing. Okay, so all these solvers, that's what is possible. Even for meshing, there are special tools. Say I can have ICM CFD, Turbo Grid, Auto Grid, Express, Gambit, Pointwise, Turbo CFD. Yes. Same way for post processing, as I say, like people, they are using some kind of solver, some kind of meshing tool, and they are doing post processing in some other tools. So these are some of the post processing tools. Okay. Now let's come to say how exactly we are using this CFD analysis for our use. So this is what is my first case study. So if you look at, this is what is experimental setup that was developed by me at IIT Bombay for my PhD. My task was to design say counter rotating fan. If you are looking at, we are having two fans. One is rotor 1, rotor 2. So rotor 1, that's what is rotating in one direction. You can say in sense it is rotating in clockwise direction, and rotor 2, that's what is rotating in counterclockwise direction. Now, if you ask somebody counter rotating, he say yes. What is new in that? It is nothing. Say two rotors, they are rotating in opposite direction, but like this is what is very complex problem itself in that case. Okay, now what I want is the wake, that's what is coming out from my rotor 1, that's what is striking on my rotor 2. What was happening in stage? The wake, that's what is coming out from my rotor, that was striking on stator. Here, this is what is striking on rotor. So you can understand the complexity of my problem. Okay, and this is what is most challenging problem. People even as on today, they are finding difficulty to get the solution. One more problem is, if you look at these blades are taller blades in the sense it's having higher height. And my chord means, if you look at from leading edge to trailing edge, what distance I have, that's what is called chord. So in order to do whole your diffusion process, you are having limited length. My height is larger and my chord is smaller. That's what is second challenge. Okay, so in order to analyze that, this is how we have done the analysis in sense. So my expected pressure rise, it was 1100 and 900 Pascal. So my front rotor, that's what is highly loaded. My rear rotor, it is say low loaded. If you are looking at, this is what is the pressure rise what we are getting from my rotor 1, and this is what is the pressure rise we are getting from rotor 2. Okay, so after number of iterations with flow physics study, with CP distribution study, we found like I'm not getting what pressure rise I'm expecting for. So in order to achieve that expectation, like this is what we have done with. So if you look at this blue color aerofoil, that's what is my original aerofoil. And if you are looking at this red color, that's what is modified aerofoil. You can say that there is a Chetan aerofoil. Yeah, that's what was developed by me in terms of my requirement. As I told, what we people used to do, say whatever aerofoil that's what is available in open domain, use that. Based on your understanding and flow physics, you need to modify your aerofoil. So basically what I have done is I have reduced my thickness and I have shifted my maximum thickness point slightly downstream. And by doing so, this is what I am getting in terms of my expected pressure rise. Okay. Now these all are the steps what I have followed. Now let me show you, say my major concern, my major requirement, it was to understand, say, experimentation. So the benefit of this contra rotating, if you are looking at, say, this is what is with, say, different chord spacings. Chord spacing in the sense when these two rotors are placed close, say 0.5 chord, 0.9 chord and 1.2 chord. Okay, conventionally what you have observed is your pressure rise, that's what you are getting, it is higher in the case of contra rotating case. And if you are looking my rotor, it is getting stalled somewhere here. Okay, so that's what is showing here. And if you are looking at this, you know, this dark one, and this is what is, say, hollow one, that's what is representing my CFD capture. What it says, my code, it is not working fine when I am talking in terms of, say, high mass flow rate condition. But for all this condition, when I am moving towards, say, peak pressure condition, it is giving me clear cut flow physics. So here, if you look at, this is what is we are saying in terms of validation. So this is what is my design mass flow rate condition at the exit of my rotor 1. So along the span wise direction, this is how my pressure, total pressure, it is varying. And this is what we have captured with putting boundary condition, what we have achieved from our say our experimentation. So it says I'm having certain discrepancy here. But when I'm talking in terms of, say, rotor 2, it says it is giving good, reasonable results. And when I'm comparing for my peak pressure condition or, say, minimum mass flow rate condition, it is capturing the results. Now, here, the question is like, why is it so? Why not here? Why not here? So that's what you need to understand. That's what we say in terms of constraints what we have doing CFD analysis. Okay, so people used to say, have you validated your code? Yes, this is what is called validation of my code. And let me share you, when I was doing my doctorate study, I went for conference in US. So NCS people, they say, please share your experimental results because we are updating our code for contra rotating concept. So, you know, like what is the value of work what we have? You know, sometimes we feel, okay, what to do with, but slowly people, they are analyzing your work, people, they are understanding your work, and then they say that's what is. So NCs themselves, I talk to them, say what is the problem here, what is happening. They say you just share your details. It's a proprietary thing with IIT Bombay, and that's what they need to understand in terms of MOU. I finished my work and left from Bombay, and now still this NCS people, they are approaching my professor for this validation part. Okay. Second work, that's what I'm working at this moment at IIT Kharagpur. Say we are having Center for Railway Research. That's what is upcoming facility. So we will be having very big size wind tunnel in which we will be analyzing the upcoming, say, your trains that will be running at 250 kilometers per hour. And in order to do the analysis for that, this wind tunnel need to be developed. Okay, so you can see this all are the requirements for us. Okay, so at the test section we are expecting 70 meter per second. That's what is approximately 250 kilometers per hour, and this is what is my test section. Okay, so this is what is a fan that was designed by me for this work. Okay, so this all are the modifications you can understand. Say we need to reduce the number of components, but you need to compromise somewhere in terms of performance. Okay, so these are the modifications in terms of my flow angles for rotor. These are the modification what we have in terms of my stator, and if you are looking at, this is what we gain in terms of our pressure rise. Okay, so now you need to understand this CFD tool we can use as for analysis. You need to be very careful. CFD is not design tool. CFD is analysis tool. Okay, that technology yet has not developed in which you will be having, say, design it will do and analysis also it will do. Some companies they are claiming like that, but still it's a question mark. Okay, so what we say, this is what is pen paper calculation what we have done. That's what is called mean line design. Then after, if you are looking at, these are the aerofoils. That's what we have developed at our own, and that's what we have used in order to design. Okay, now this big fan, this fan, let me tell you, that's what is having diameter of 4 meters. So you can imagine how big that fan is. No one in India at this moment ready to make that fan. And before my joining this project, it was started in 2013. The group, they approached to some of the foreign companies, and they said like the design and fabrication of this whole fan, only fan I'm talking of, that is 10 crore. And the whole project cost, it is near to that. So that's where, like, you need to have that technology, you need to have that understanding. So after my joining, this is what is the first project I have done successfully in terms of design. Now there are few fabricators they agreed upon from India. They will be doing their work outside and bring here, and they will do assembly here with our design. Next work, this is what is my PhD student he is working on. So as I told, like, suppose say if I'll be having this as my aerofoil. Okay, for that aerofoil, if I'll be increasing the curvature, my delta beta, say beta 1 minus beta 2, then I can extract more amount of work. That means I can have very high pressure rise. But what is happening? Because of your adverse pressure gradient, there are more chances for my flow to get separated. You can see this is what is the flow separation. That's what is happening. But like when I say for my engine, if I'll be having, say, 12 stage of compressor, let's discuss in terms of now application. Say for aero engine, suppose my compressor stage, it has 12 stage compressor. By some mean, if I'll be reducing one of the stage, say in place of 12, I'll be reduced, say 11, what will happen? My assembly, in sense, say the weight of my rotor, weight of my stator, that will be reduced. Same way, length of my shaft also will be reduced. So in overall, what we can say, I'm reducing the weight of my engine. When I say I'm reducing the weight of my engine, then overall drag on my aircraft, that will be reduced. That means it will improve my fuel economy. Okay, so that's what I say. Like for aerospace engineers, we are the people who are talking more in terms of, say, reduction of weight, or what we say in terms of lightweight, or we used to say compactness, so reduction in the size. So what is the whole idea here? Here we have splitted this aerofoil into two aerofoils, say one aerofoil and second aerofoil. That's what are placed in tandem manner. That's why it is called, say, tandem aerofoil. So if you are looking at what is happening, the whole flow separation, what was happening because of large turning, that's what has reduced. So this is what is the work we have targeted with. And you know, when I am talking, this is what is, say, 2D aerofoil, or it is at particular section. We are talking of rotor. Okay, so for rotor, if you are looking at, say, this is what is a base rotor configuration, in which pitch, in the sense the distance between, say, in circumferential direction, you need to understand, in circumferential direction, I'll be having that distance as, say, 82%, and axial overlap, that means the overlap of exit of my rotor 1 and entry of rotor 1, that's what is 0. When I say -5, I am having, say, +5, and here I am having, say, 3%. So you can see how these arrangements are. Okay, now here you need to understand what is the reason why we are having. So what is happening, my flow, that's what is coming here. Since this is what is having, say, low turning, that's the reason chances for my flow separation, it is less. Now in between this passage, you can see that's what is having, say, nozzle shape. So what it will do, it will accelerate my flow on this my second blade, and that's how it is delaying the separation of my flow on this surface. So that's what is the whole physics here. Now we have gone with, say, understanding of physics. Here if you look at, when we are having 0% axial overlap, what is happening? Say, as I told, we are getting the benefit in terms of this nozzle effect, but at the same time I'll be having large flow separation. That's what is happening near the tip region at 70% chord. Then we tried to analyze using, say, -5%. So you can say my rear blade or this backside blade, that's what is moved inside. So what we are getting certain benefit in terms of rising, say, velocity, but you know, I'll be having more problem. Here I'm having great separation. That's what is happening near the tip region. Even my rotor 2 is also getting stalled. Okay, so this minus or the movement inward, it is not visible one. Then we have analyzed with, say, third case, what it say, +5%. Just try to understand. Here also we are getting the benefit in terms of, so whole my rotor 2, that's what is working under unstalled condition. And here in this case, I'll be having my flow, that's what is separated towards the trailing edge, maybe 80% span. Okay, and you need to understand what pocket we are getting. This pocket is nothing but that's what is the flow, that's what is coming from this tip gap. So it is not because of aerofoil, this is what is because of what is coming from the jump. Okay, so this is what is this particular patch. And if you are looking at, then we have analyzed in terms of what exactly we are getting, and we found like +3% axial overlap. That's what is giving the benefit in terms of physics. Just look at what is happening near the trailing edge of my rotor 1. Just look at here. Then what is happening with my rotor 2? Here in this case, here in this case, here in this case, here in this case. So now what we have at the exit, my flow that will be coming out with, say, this kind of vortex. This is what is called, say, combined vortex. That's what is coming out from my passage. And here if you look at, this is what is because of my nozzle effect, I'll be having, say, acceleration of flow. Okay. Now I was discussing because of tip leakage flow, I'll be having this low momentum fluid. That's what will be present. That will be impact on my stator. So we have analyzed this rotor separately and we found it is working fine. Now the question is, this is what is entering inside my stator. When it is moving towards the stator, it is let my stator to work under off design condition. And that is what is not giving what expected pressure rise we are looking for. And in order to accommodate this loss, what we are having, if you are looking at, this is what is blockage loss. that loss we have reduced by using, say, different 3D blading here. So here if you look at, we are having lean here, dihedral we have done near this hub region, dihedral we have done near this tip region. Okay, and by doing so, what we are getting is, in terms of, say, my flow to be as per my requirement. But still what we have found, like if you are talking in terms of exit flow angle, like when I'm doing my design for stator, I say whatever flow, that's what is coming out from my rotor, that will be striking on my stator. That's what is possible when I'm having only one blade. Here in this case, these blades are under tandem configuration. So I'll be having two wakes, that's what is coming out from my rotor. Okay, so two wakes that will be striking on my stator. So if you are looking at, say, this is what is coming out from my, say, front blade, this is what is coming out from my rear blade. Okay, and this is what we have captured using the physics. What it says, for particular region, this is what is working fine. Other than that, it is not working fine. And that's what is a problem to us. Why it is a problem? Because you just understand the flow, that's what is coming out from my rotor, it is striking on my stator, and that's what is changing my physics. So in order to analyze, we have modified our angle. We have taken the average angle here. And when we are taking this average angle, just have a look at, this is what was my first case. I was having very great separation. That's what is happening on my suction surface. So you can have, this is what is conventional part. Now when I'm talking in terms of modifying with using, say, dihedral, what was happening? Say this is what is, say, dihedral. So even I'm able to manage my flow here at the exit, but still it is not as per my expectation. You can say this is nothing but the low momentum fluid. It is acting like a loss. So in order to avoid that possibility, what we have done, we have changed the angle. When I'm changing my angle, that's what is giving me my exit like this. This is what is most challenging design in itself. Okay, so when you are reading paper, when you are doing the work, it seems like it is very easy work, but when you are working on actual problem, this is what is one of the solution what we have given to the society now. So based on this, now we are having rotor and stator under fabrication, and very soon we will be doing the experimentation. Okay, that's what is a unique facility available in India at this moment after Germany. Germans, they have done this work, say, in 90s, and then they stopped working on that. Now we have taken that as a challenge as per the requirement. Okay. Next work, that's what is going on with my second PhD student. He is working on, say, variable area turbine nozzle. So if you recall, I was talking about, say, 6th generation aircraft in which it is a smart engine. What you mean by smart engine? When my engine, it is working under design condition, everything, each my component, that's what is working fine. But when it is working under off design condition, suppose, say, when it is working at decreased mass flow rate or increased mass flow rate, under that condition, I'll not be having good aerodynamic matching with compressor, combustion chamber, and say, turbine. Okay, now in order to maintain my rotational speed of the compressor constant, what will happen? Suppose, say, my mass flow rate, it is decreasing at the entry of my turbine. What it will do, because my passage area is constant, it will not let acceleration to be happen. If it is not accelerating much, it will not generate sufficient amount of power to rotate the compressor. That means my rotational speed of the compressor will reduce. Okay. Now I need to have certain kind of mechanism with which I can manage my mass flow rate. So that's what we are doing with. Say here, if you look at, this is a pivot end, and I'm making this as a variable area. Okay, so let me show you here. So this is what is the data. As I told, nobody will share any details about any engine, any component. So it's a challenging part when you start doing the research. We got one of the report, that's what was by NASA E3 engine. As I told, GE and Pratt & Whitney, they have given separate idea for. So this is what is the engine data available for Pratt and Whitney. So we have selected this one for our analysis. Okay, and for that analysis, we are having all profile data near the hub, near the shroud, and in between. So based on that, we have developed this profile. You know, like leading edge and trailing edge for compressor or turbine, it is always very challenging, and that's the reason why people, they will not share any data about the shape of leading edge or trailing edge. So with number of trials and error, we got this profile. Now what we want to do, I want to develop the technology for say variable area. Okay, now in order to have that variable area, if I'll be talking, say I have this passage, this is what is my original flow passage. If I'll be putting this variable area and if I will try to rotate it, then you know my blade vane that will get stuck here, and here I'll be having great gap. So that's what is not serving my purpose. Okay, so in order to do or implement this kind of technology, I need to have parallel wall kind of configuration. So whole this passage, that's what has been redesigned with CFD analysis, and we are able to achieve same pressure rise at the entry of my rotor, entry of this nozzle vane. Okay, with minimum losses at the exit. Now in order to make this motion, we need to have circular end or elliptical end. You just understand, I need to have certain amount of clearance between this solid wall and this wing. If it is not so, then I cannot rotate my wings. Okay, so maybe it is little tough for you to understand, but you just take it as a granted. Okay, now you can understand here, this is what is my wing. Okay, so here if you are looking at, I am having this as end, this is what is my second end, and this is what is my wing. Now what we are doing, as I told, we are changing this area between this passage. Okay, so this is what is one blade, so original position, I can move in this direction, so the passage area I am changing here. Okay, now the question is, sir, like this is what is new in this. Now the question is, we have kept certain amount of clearance here. When I say clearance, what we are incorporating, that will subject it to loss, tip clearance loss. Now this tip clearance loss, what we have, okay, so what tip clearance what we have, in sense, it will reduce my performance, it will deteriorate my performance. Okay, when I say when it is deteriorating my performance, then it is of no use to use this for my requirement. Now the task is to minimize those losses in the clearance area. Okay, let me move to the next slide. If you are looking at, this is what is without pivot condition, you can say these are the streamlines, that's what is coming from pressure side to the suction side here. Same way, this is what is near the hub region, and this is what is near the tip region. Okay, and having this roll up, that's what is happening at this particular location. Here in this case, my roll up, it is happening at 70%. Now what I am using, I'll be using say pivot point, that's what is say here I'm using circular one. Just look at how the physics it is changing. What it says, because you know, like part of this upstream that will be merging in downward direction here. So my flow is trying to move more towards my suction side. Similar situation is happening here. Okay. Now, when I'll be using say my elliptical end, you can understand what is happening. Say it will be having no upstream merging, that's what is happening, and I'll be having this streamlines, that's what is moving away from my surface. Okay, and this roll up, that's what is happening at 84%, and this is what is happening at 80%. Just try to understand what we are analyzing here. In this case, if we are talking say 70% chord, so at the exit I'll be having very large secondary flow, that's what will be coming out. When I say it is placed at say 84% of axial chord, you can understand the wake, that's what will be coming out, or secondary flow, that's what will be coming out.
that will be of small volume. Okay, now the question is like, what will happen if I want to minimize the losses? This is what is happening. So this is what is one work. Okay, and this experimental setup, that's what is under development, and we will be doing the experimentation for that. Okay, now this is what is one of the student project. I have 25 students, they are working on this student project. The whole purpose here is to develop, say, your flying car. Okay, and that too, it's electrical flying car. Okay, at this moment we are talking for say 10 kg weight, and this are the fans what we'll be using in terms of say electrical propulsion. So you can say this is what is when I want to have lift up. So all my fans that will be facing like this, and exhaust that will be striking on the ground. When I want to move in the cruise condition, I will be tilting my fan in this position. So the task is like, at what distance I need to put these fans and how many fans I need to use. Okay, so our study that says if I'll be using say single fan, then I'll be having more weight, I'll be having more power consumption. And if I'll be using multiple fans, I'll be having say less power consumption and weight also will be less. But the question was where to put these fans. So this is what was done by CFD analysis. Okay, and we have found like there is a certain distance between these two ducts we need to put. This is what is the analysis using the rotor and whole engine analysis. So this counter-rotating part that has its own benefit in terms of increasing or decreasing the pressure rise. You can see when both the rotors they are rotating at low speed, ND it is design speed, I'll be having low pressure rise. If it is rotating at high speed, I'll be having different case. Okay. So this is one work. Now this is what I was talking to you in terms of say inverse design. Just try to understand here what we are talking of. Say we are having impeller and this is what is diffuser. So they have done flow visualization study like what we used to do in our CFD analysis. The experimentalists they are using flow visualization. So here if you look at, they are having say there is a separation bubble, that's what is happening here, and that's what is deteriorating the performance. So task was to improve the performance. So if you are looking here, this is what is the conventional design what they have, in which this is what is creating the trouble in this particular region. Then based on their flow physics, based on CFD and experimentation, they propose with say inverse design. And what they have done, they have modified the profile here. Let me show you the profile. Just look at, this is what was the original one and this is what is the modified profile. Okay, so you do your experimentation, good flow visualization, and you can have like results similar to what you are talking in terms of CFD, or you use your CFD. Now the question is, say you already have something existing with you. Now you say, suppose I'm having say my compressor, that's what is having pressure ratio of 1.2. I say I want to increase that pressure ratio to 1.4. So I can use this tool, that's what is called inverse design tool. It is nothing but that's what is based on your understanding. Okay. Now there are certain bio-inspired turbo machines also. Like here, if you are looking at, this is what is a mixed flow compressor kind of thing. They got inspired with this surface, serration surface, that's what was on well. Based on that, they have modified the suction surface profile on the blade. Okay, what you can see here, I am having say higher kinetic energy, turbulence kinetic energy. By providing this kind of configuration, they are able to break down those vortices, and by mean of that, they are able to reduce the noise. So noise is also one of the criteria for the design. This is what is say inspired with say your shell people, they made new kind of impeller, that's what is say Lily impeller. If you are looking at, this is what is say Sept propeller, the purpose is to increase say your thrust value. Okay, what they have done the serration on the leading edge. So this is what you can say, we are having leading edge. Okay, similarly this is what they have implemented in the case of say your aircraft propeller. They have modified the leading edge of aircraft propeller, and that by that mean they have increased the thrust. Okay, now this is what is a work by say University of Cincinnati. They got inspired with this eagle winglet, what you are looking at. So what they are proposing, they have modified the end of this tip. What we know, if you are able to manage the tip leakage flow, you are able to increase your performance, or what we say in terms of your operating range, or what we say in terms of your efficiency. Okay, similarly these days we are having many fans what we are using for say our servers or computer. That's what was making a lot of noise. Now people, they have used the serration technology. So this is also turbo machinery, and there also people, they have used this in order to reduce the noise. One of the most recent work, that's what was given by say this counter rotating open rotor kind of thing, in which they have used this serration configuration on the rear side. So you need to understand, like once you are having this tool, CFD tool, you can do number of iterations. Once you get the confidence in terms of the accuracy of the results, you can do iteration. Based on these iterations, you can develop your prototype, you can develop your model, and then after you just do testing if it is meeting with requirement. So basically CFD tool, people, they used to say it's design tool, but it's not a design tool, it is design iteration tool. You need to revalidate, you need to re-say like that. Now if you are looking at, these are some of the works, that's what is going on in terms of say casing treatment. You can understand here, this is what is a fan, big fan, and here you are having casing treatment. So for this casing treatment, there are different suggestions by different researchers. So if you want to implement that for your case, let me share you, I don't know whether I told you or not. See, all these compressors, all these turbines, what you are looking for particular engine, that's what is a unique for that engine only. It is not like say we are having two-wheeler. Say if my carburetor for Hero Honda is not working, I can replace that with some other vehicle. It is not like that. It is indigenously been developed for individual engine and for individual component. And that's the reason why your costing for that component, it is very high. Okay, when we say very high, single engine, that's what is costing maybe 200 crores, 300 crores. And that too, they are selling at loss. Maybe someday we will discuss all these things, but this is what you can reduce your iterations. Based on your results, you can develop and you test your facility. With that testing, you can go ahead with your confidence. Next, one more thing is in terms of say inflow distortion. As I told, when you are having say takeoff, some of the flow that will be going upper side, it may be possible you will not be having flow, that's what is going downside, and that's what is acting like an inflow distortion. Maybe when you're having say wake, that's what is coming out from your front aircraft, you will be having say condition in which you will be having say turbulence. All this subjected to say inflow distortion. When I say inflow distortion, that's what is very tough. Okay, and that's what is a challenge for your engine. If your engine is not working fine, it will let you down. Okay, so these are the experimental results by me. If you are looking, this is what is particular patch, low pressure area, that's what is representing the distortion. When my rotor, that's what is rotating and in say anti-clockwise direction, this it is getting distributed here. When my second rotor at the exit, if you are looking at, it says whatever is my distortion effect, that distortion effect, it is getting nullified. And that's what has given new idea, new concept to new designers now in terms of engines. So now people started talking in terms of distortion intolerant fans or distortion intolerant say compressors. Let Let me show you one more result here. Say this is what is the upcoming kind of aircraft, wide body aircraft, in which your engines will not be placed on your wing, it will be placed here on the fuselage. You can understand I'll be having the growth of boundary layer, that's what is all the way from this surface, and that's what is getting inside. So inside this engine I'll be having my distribution like this. This is nothing but it says my say distortion. So Whittle Laboratory, Cambridge, they are working on design for this fan. Okay, and here if you look at, this is what is they are getting with their measured value, and this is what is with their say computational value. You can understand, like this is what is say actual what they are getting. This is what we say in terms of computation. It is under predicting or over predicting certain flow physics. And based on this study, they have modified the stator. Just look at the stator. You know, there is a particular region of stator, that's what they have modified in terms of design. Okay, and with this modification, if you look at, they are able to manage the flow at the exit of their stator. Okay, so this is what is more uniform flow, that's what is coming out at the exit of my stator. So you can understand inflow, that's what is flowing inside this fan, so that's what is subjected to problem. Now that's what is transferred to the stator, and downside I'll be having say another engine, that's what is subjected to distortion again. To avoid that kind of situation, this is what is new coming technology people they are working on. Okay. Next problem, that's what is with say turbomachinery noise. You can understand, say I will be having upstream distortion, I'm having say tip leakage vortices, growth of boundary layer, I'll be having wakes, that's what is coming out. So all this together, that's what is giving large noise. If you are looking at here, this is what is representing the noise, that's what is generated by the fan. So now as per the guidelines, very soon these airlines will be restricted to use certain kind of engines which are making large noise. Okay. Then next challenge, that's what is coming with the bird strike. Okay, you can understand here this aircraft, what it will do, it will maybe one or two that will go inside, that will damage the blade. You can understand here, this is what is the undamaged sector, this is what is the damaged sector. Now people they are expecting this CFD or this analysis fellows to do analysis for engine. If my blade is getting damaged, what will be the effect downstream? Yes, this is also, so just look at here, if you look at, this is what is with say your damaged blade configuration. So what is it is doing, because my blade shape, that what has changed, that's what is changing my physics here. Okay, so you need to be careful. Now next challenge what we say is in terms of say blade cooling. Okay, there is a disturbance, can you please put you on mute? Okay, now here what we say, this is what is my blade, and in internal structure I'll be having say small holes. Now the challenge here, it is to do meshing. You can understand this hole, it is of say maybe 0.4 mm diameter or maybe 1 mm diameter, and that too there are many, and inside passage. So here what we say, this is what is very complex physics that will be happening within the passage and even outside also. So this is what we say in terms of the challenge for your CFD. Now, as I say, there is a cooling mechanism. So I'll be having the high pressure air, that's what is we are taking from high pressure compressor, that will be getting injected in my blade, and that's what is coming out from these holes. Okay, so like you need to design this kind of passage. That's what is required, very good understanding in terms of flow physics. So there are engineers, they are only designing this secondary ducts or secondary flow analysis. This is what is called secondary flow analysis. Okay, so here if you are looking at, I'll be having seals, I'll be having reams, that's what is present, and in that my high pressure air, that's what is going inside, and you need to be careful the hot gas that should not enter inside this passage because of temperature difference. You can understand. Okay. Then there is one more realistic problem. Let me show this. I don't know. Let me show this. Just have a look at. So this is what is, say, ice ingesting inside the engine. Just try to understand. This is what is a real situation. That's what is happening these days for, say, European Union, mainly for Western region. Just look at what is happening. So this small ice particle, that's what is passing through rotor, but that's what is getting stick on that stationary surface here. Okay. Now what it was doing, just look at here. Some of the portion that will get peel off, and that's what is entering inside your later stage. Just look at, this is what is, say, your blowdown of engine, and that's what is a failure of your engine. Okay, so that is also one of the challenge to analyze this kind of situation. Next challenge, what we say, is volcanic ash. Okay, so you know you will be having flights, and what volcanic ash particle, that's what is flying, that may be going inside your engine. So here if you look at, this is what is happening in sense. Just look at, this is what is with, say, turbine nozzle. Now you need to analyze your engine under this condition. Means suppose that this is what has happened, what will be happening next to the engine. Okay, over the time your surface that will get ruffled. So your irregularity that will be coming. So when I say surface irregularity that will be coming, your whole growth of boundary layer, that's what will create the trouble. Okay, so all this, they are coming into the challenge. Now the next challenge, big challenge, what I say, is to analyze the whole engine. You can understand this is what was the fullest project. It is LES, as I was saying. They have done full engine analysis using LES. So this is the kind of work now people they are expecting from CFD. Okay, so that will give clear understanding, clear idea in terms of what exactly is happening. Okay, then let's move towards, say, other applications. If you are looking at, this is what is my steam turbine power plant, and here if you're looking at, people they want to reduce the size of this to this. Yes, that's what is possible with, say, supercritical CO2 cycle. So my working fluid is not steam or not water or it's not air. I'll be having, say, my working fluid to be different. So it itself is a big challenge because my properties, that's what is changing. When my pressure is changing, my temperature is changing. So it is making that case very complex. Even when we are talking in terms of, say, organic Rankine cycle. So, you know, this is what is small power plant, what people they can use for auxiliary power generation. Then people they started talking in terms of, say, counter-rotating technology. They have various applications, say, fan, turbine, pumps, tidal pumps, okay, and this kind of, say, engines. Now, in overall, if you say, let's try to come to the concluding part. What it says, what are the advantages of CFD in turbomachine application? What it says, this is what is extensively been used for design and analysis purpose. The accuracy of CFD is slowly rising. The acceptable computational resources permitting the simulation for high-speed flow, that's what is required, say, high fidelity technologies. Okay, to control the unwanted features like strong secondary flow in turbines or the corner separation in, say, compressor, CFD has ability to predict this kind of three-dimensional nature. Modern turbo machinery design, that's what is mainly been relying completely on CFD. Okay, so that's what is, so companies now they are more relying in terms of analyzing the physics by using this CFD tool. We can able to predict like change in the direction of flow with more reliability, and flow three-dimensionality also we can use. Using CFD study, the distortion can save the time and cost, and during early stage of design, we can process for the compressor. Let me share you here. Suppose say you already have idea about say what is happening with your say distortion. If those results are available with you, you can do your iteration for design in which you can make distortion intolerant fans or distortion intolerant compressors. Okay, that's what that Cambridge University they are working on. What are the issues? Say it is three-dimensional CFD calculation in compressor blade is still not good accurately in order to calculate the total pressure loss. Means the physics it is not clearly being captured because you are having all kind of flow. That's what is happening. CFD cannot accurately estimate the loss prediction, and understanding of its result need great skill and experience. That's what I say. You need to be very thorough with the subject, and then only you jump for this turbomachinery part. So over the year you will get matured with what is going on, and then you will be having your own expertise. The CFD design optimization, the peak efficiency that has increased by 2.2%, but still it is lower than the expected 1%. Okay, so numerical error it is completely obtained by utilizing commonly been obtained utilizing say CFD due to finite difference approximation. So if you say I'm using say steady state analysis, I'm using say RANS, that RANS it is having its own limitations. Error involved during the modeling where the true physics is not well known and it is well complex to model like turbulent modeling. So you know like the geometry what you will be using that need to be clearly be known to you. You need to be clearly understood. And when I say turbulence modeling, you can understand at entry of my compressor, in between compressor, at the entry of my combustion chamber, at the exit of my combustion chamber, at the entry of my turbine, at the exit of my turbine, this turbulence intensity that's what is changing. Okay, so you need to have proper understanding of how it is changing. Grid dependence analysis is a fundamental task for CFD for numerical as I told, but grid spacing affect the reasonable for the merger calculation for both flow structure and integral parameter. The effect of computational grid must be accounted while performing your high fidelity CFD. Prediction of highly turbulence flow, that's what is depending on what turbulence model you are using, and that's what is putting constraint to your code. Major limitations we can say heavy computational demand for design and prediction of flow for compressors and turbine that will lead to say very time consuming and it is very costly affair. For accurate numerical prediction of say turbulence, unsteady or non-uniform heat generation lead to say augmentation of your simulation time as we have discussed like when we say convergence. Memory requirement for the CFD code for the iteration of the results need to be reduced in order to have when we are having say a truncation error that's what is more. The programming for complex flow situation is a real test of computer skill. Yes, this is what is most challenging part. You know, you will find rare people those who are doing coding for turbo machines. You can find number of people they are using commercial code for turbo machines with or without understanding. Okay, so the maintenance cost for the huge CFD program developed for the investigation of multi-stage turbine or compressor is also high. You can understand the people they have analyzed whole engine, how much computational power they are looking for. Then it says the recent trend for CFD is shift towards a unsteady and multi-stage prediction which need amplified computational power. Unsteady simulations are not yet much time consuming that is not used for say routine design purpose. So you can say like when I say I want to design say industrial fan, I'm not looking for the unsteady flow physics in that condition. I say okay my steady results are okay with. So unsteady simulation, the total execution time, even using say multi-processor or multi-CPU, it is very high. To analyze and improve the design of turbine compressor, engineer need the complete computation overnight. It is very difficult. You know, like for Indians, we have tendency, we say like, you can use your CFD and give me results within 2 days. So it is not like make food. Okay, you need to understand this case. This is what is required, too much understanding in order to solve the problem. Okay, it requires too much detail. You need to have so many understanding in that sense. Then only you can go with analyzing this part. There are few pump manufacturing companies, they approach when I was at Nirma University. They say, sir, can you please help for redesigning our pump? I say, okay, fine. Sir, how much time will it take? I say, okay, maybe it will take, if you will give everything in terms of geometry, and if you want to modify it, maybe it will take 2-3 months. No, can you please give next week? It is not possible. It is not a joke. You need to understand that part. Okay. So now next generation CFD software, what all we are looking for? Say total flexibility with regard of complex geometry. So meshing need to be very easy. So reduce the grid generation task required from the user. This is to be done possibility by using say automatic grid generator or adaptive solvers. Highly accurate, robust, efficient solver, that's what is required, with second order accuracy and very fast conversion rate for steady as well as unsteady rotor stator interaction. Overall, it should have robustness and reliability. It should be adopted for large scale computing facility, rigorously valid with the physical model of turbulence, combustion, multiphase flow, including their range and validity. Allows for multidisciplinary applications, say like I want to do conjugate heat transfer, I want to do aeroelasticity, I want to do aeroacoustic. You need to understand like what CFD analysis, what we are doing. Maybe Professor Sonawari, he will discuss in more detail when he will be discussing about fluid structure interaction. So you know what results you have from this CFD analysis. That's what is in terms of say pressure distribution. I can say I can consider that as a force, and that I can put on my FEM analysis as a force. I can able to do aeroelasticity analysis also, and that's what the companies they are doing. Then it says efficient post-processing and focused graphical quantitative analysis tools for large scale unsteady simulation, maybe LEOS or DNS. Integration of CFD tools in efficient optimization environment. Although all these topics are subjected to large efforts of research and development, much progress is still need to be to achieve these all objectives. Okay. So if you look at so what we have discussed today, I think I am able to convey the message in terms of what all are the applications and challenges of CFD analysis, particularly for the turbo machinery. What all we have discussed, I have started with your introduction part and fundamentals. Then we were discussing about say the question what we were having, why, what and how. Then we have discussed certain say case studies. We have discussed about the advantages of CFD, the issues and challenges what we have discussed, and we were discussing something in terms of say next generation CFD demands. So as I told, the necessity, it's a mother of this invention. And if you are looking at say applications of these turbo machines for say aero engines or say your land-based power plant, we are having so many research activities. That's what is going on. That's what is say ranging from say 1 to 17, maybe many more. Okay, so what all blue portion you are looking at, that's what is the area where I am working at this moment. Okay, and still to run with. Okay, so let's say thank you very much for this talk. Thank you very much for hearing. Okay, and now this session I say it's open. If Professor Sunavane permits, we can say this session is open for the discussion. If you have any query, we can discuss.
Yeah, thank you, Dr. Chetan Mistry, sir. It
Yeah.
was really informative session actually. Even myself, actually, I have not thought of all this kind of turbo machinery stuff.
Yeah.
Yeah.
Thank you. Thank you.
Even during our BTech, we do undergo some kind of turbines and all those things, but not in details.
Yes.
Yeah.
Yes.
So those CFD required some extra things which you today provided. So thank you very much. Yeah, I think Atul Tumane is raising hand, so you can unmute and ask your question. Atul.
Sir, my question is, in case of
Yeah, go ahead.
Kaplan turbine simulation, hello sir,
Yes.
Yeah, go
Yes.
ahead. Go ahead.
in case of Kaplan turbine simulation, if we
Okay.
provide boundary condition as velocity inlet condition, and if I had to check pressure distribution between suction and pressure side in our post-processing result, and want to see result for rotor momentum also. So how much amount of rotor resolution and all that I have to see with this boundary condition, then is that possible that in that case I will see my post processing result, how much momentum that rotor will gain, and what is that a part of fluid solid interaction that I have to ask, sir?
No, that is not fluid solid interaction. Yes, momentum. You can calculate the momentum. You can calculate what is the amount of power. That's what is generated when you are saying in terms of turbine. That's what is possible with. So you can do that kind of work. Yes.
So which software, sir, in that case I can use for that?
See, I can not name in open domain when we are at say at this
No,
platform.
about
There
open
are
source tool
many.
also you can suggest, sir.
Yeah, even in open form you can use say commercial packages what are available, say ANSYS you can use Star CD, many softwares they are available, so you can use that part.
So rotor
Okay.
momentum I can see, sir, in that case.
Yes, you can.
Okay. Thank you, sir.
Yeah.
Okay, Dr. Umesh Poddar.
So, I'm Umesh Poddar from Pune.
Yes.
So generally, we prefer to validate the CFD result with the experimental results. But in some case, if experimental results are not available, is it a good practice to compare with the earlier computational results or literature?
Like when we say in terms of validation, it is preferred that you need to have the data from say experimentation, and that's the reason why I told, like, companies mostly they are spending a lot of money in terms of research and development, in which they are spending whole lot of money only in experimentation. So without, say, what is your purpose, that's what is important. Like you are talking in terms of say rocket, say flying rocket, that kind of, you will not be having any experimental results available for that. So the kind of application what you have, based on that you need to decide with.
Okay, sir. Thank you.
Okay, any other questions from the participants?
Hello.
Yes.
Yeah, ma'am, go ahead.
Sir, I want to know about feasibility of machine learning algorithms in complex machine part for turbo machinery.
Yeah, as I told, like all your devices what you are having, all say compressors, you might have seen, like for say transonic compressor, my profile near the hub, it is subsonic profile. My profile near the tip, that's what is transonic profile. So there is no universal as such rule in terms, but yeah, people they started using say machine learning in order to analyze this kind of results. You need to explore more. Yeah. So
Thank you, sir.
what? Yeah. Okay. Okay.
Okay, any other questions from participants? Okay, I think Dr. Chetan Mistry, sir, thank you very much, sir,
Thank you.
for
Thank you
your
very
nice
much.
interaction and all those things. Okay, definitely we will invite you for more and more such kind of functions, and let's have
Sure.
some more interactions in terms of maybe we can have student gathering or even some kind of expert lectures.
Sure, sure.
Okay,
Most
sir.
welcome.
Thank you.
Yeah.
Thank you very much,
Okay.
sir.
Thank you very much. Thank you all. Enjoy this course. You know, this course